السلام عليكم ورحمة الله وبركاته. حياكم الله في البرنامج التدريبي. Welcome in the training program entitled Virtual Hands-on Training Measuring Analog VLSI Circuits with Mr. Vipul Sharma. So please, Mr. Vipul, you can start the training.
Okay, thank you, Dr. Salman, and welcome everyone to this training on Introduction to Analog VLSI Circuits in open source IC design, and also how to test those circuits. So the main emphasis of this training is to basically understand actually when we finish our designs, the chips got fabricated, our circuits get fabricated on a silicon, and when we get back those chips or test ports, how do we actually design test those circuits? So that is the main agenda of this training. And before that, I will just give you a brief introduction of analog VLSI design. Basically, what exactly is VLSI, what is analog design, what is semiconductors, and what kind of approach we generally use to design those ICs, because that is also important. I think I have covered these topics in few of the previous trainings organized by SSP, and some of you might be part of that training also, so must have benefited of them. But once we complete our designs, what happens to those designs? Because ultimately, whatever we get fabricated on silicon, we need to test whether they are performing as per the requirements. So that is what we will learn during the course of this training, and we will do that basically using actual circuits on silicon. These circuits were designed previously using this same approach, open source IC design approach, and now we have those chips with us. And during the course of this training, in next few lectures, I will show you the theoretical part of how to do this training, what kind of equipment we need to use. And then later on, once the training completes, we will be having some online sessions where you can book the slots and try to test online, remotely, those circuits. So that all things I will be covering in the current lecture and maybe future lectures. Okay, so let us start with. So what is the basic objective of this training? So the basic objective is to gain the knowledge of VLSI circuits. So basically understand like what actually VLSI design is, what is CMOS technology, what are semiconductors, but it's not limited to that. Once a designer does his design, he does his all the design steps, tape outs his design, and send it to the fabrication or unit or a foundry for fabrication, and then gets back his chip. So next, what he needs to do, because some kind of testing needs to be done, like whatever things he designed during the phase of simulation or schematic or layout stage, are those things working properly after fabrication on silicon? So that is what we will try to learn as part of during the course of this training. And what is the expected outcome? So the outcome is like I will be giving you an example of few four basic analog IP blocks, like an operational amplifier, single stage amplifier, bandgap reference, oscillator. So all these are building blocks of any analog IC or VLSI circuit. So we have those circuits with us on chip on silicon, and now we need to test those circuits using a particular measurement setup. So that is what we will learn during the course of this training. Okay, before moving forward, let me just give you a background, like why testing is important. We all have heard about like what is the importance of semiconductors in our day-to-day life in global domain. Like everybody is talking about semiconductors nowadays. So obviously, for semiconductor manufacturing of semiconductor, you need foundries or big fabs where all the manufacturing takes place. But then somebody has to decide like what actually gets manufactured inside that foundry or on that silicon wafer. So that is the role of IC designer. So IC designer does his steps. He basically conceptualizes the circuit, builds his architecture, and then follow all the design steps to finally tape out a design and then send it to the foundry fabrication. But there is one more step which is critical, and that is to post fabrication steps. Those are the IC packaging, bonding, assembly, and then testing. Okay, so the packaging, bonding, and assembly are not the part of like scope of a designers, because those activities are specifically handled by a ATMP unit, specialized setup, similar to foundry but not as complex as foundry, who understand those steps and implement. They takes a silicon die and assembles it in a package and finally outputs as a final product from their manufacturing unit. So that is the role of ATMP. But once that is done, somebody has to test those circuits, and there are specialized approaches which needs to be used to test those circuits. And there a role of designer also comes. And testing in itself is a dedicated career option because test engineers they have their own specialization. They know about what kind of equipment needs to be used, what kind of signals need to be applied. If it is a digital design, then testing approach is different. If it is analog, it is an RF design or MEMS design or some kind of a optical design. So every domain has its own testing requirements. So that's why testing itself becomes a very critical step. And there needs to be specialized training or specialized people who perform those steps. It's not like a designer can do it. But once you are a designer or you are a test engineer, these both domains are very much correlated to each other. Whenever a designer does his time, he is dependent on test engineer, and test engineer is also dependent on a designer to make test plan because he needs to understand what kind of circuit lies inside a IC or a silicon on silicon. For that, he needs a feedback of a designer. So somehow these two domains are somewhat correlated. So it is important, like if you are interested in semiconductors, if you are interested in VLSI design, it's good, like you should have some basic knowledge of testing. And that is our motivation so that you people can get basic understanding of like testing in itself is a good career option if you want to make a good career or you are interested in semiconductor industry. Okay, so now let us start. Before starting, this will be our schedule of our training. I think it is already shared with you. This is the kickoff lecture where I will be just going through the basics of analog VLSI. And then in rest of the remaining lectures, I will take one circuit one by one and try to explain you through presentation, like how we will undergo the testing. And once those lectures are complete, you will follow the instructions which are given in these slides or my lectures and try to implement those testing during the remote setup plan. So that is our schedule and how we want to plan through it. And these are few guidelines. So I think these are important. So just focus on whatever I talk about now. So what happens is once my lectures are complete, post lectures, you will be basically booking the slots will be around a 45 minutes time slot will be given to you where you can log in through a Teams meeting link. For that you need to book your meetings through this Calendly link. This is an online app where you can book the meetings. You will receive a link, and on that link we will basically interact with each other, where I will give you a remote access to my system and my testing setup, and you can try to play with settings of a measurement equipment and try to make measurement on these circuits. So that is how you basically, after the meetings, this link will be enabled after the lectures, and then you need to go through that link and find the slots where you can book the meetings. Okay, as part of a testing, when you will be asked to test, you should, while booking the slot of a meeting, you need to select like which particular circuit you want to test, because there are 4 analog circuits, so that once you give me your preference to test a particular circuit, I can make that physical setup available at my end. So that is, please, you need to note down, like you will see that option while booking this meeting link. You please enable that option, select that option, and so that I can make a setup accordingly. And during each testing slot, only one circuit can be tested, because testing itself is a time consuming process. So it's not possible like in 45-minute time slot, you can do multiple testing of multiple circuits. But if you want to test more than one circuit, then you can definitely book another slot. And for if post these lectures or during the course of this training period, whenever you have any queries, you can post your queries to me through Slack. Slack is basically a communication platform where you can join that Slack channel and post your queries. It is a community platform where I will be available. I can answer your queries, or if somebody else within this community knows answer, he can also respond to your queries. So that's where we will be communicating most of our queries, and any discussion or any doubt you have, you can post your queries there. And for joining the Slack, you please fill this online form where you will share with me your email ID, and I will send you an invitation to join that Slack. So that's how. So basically, you need to remember about these two things. So first, I think you need to do is to fill this online form so that I can make you part of their Slack channel, and then we can communicate over that. And then later on, once the lectures are complete, you need to book your meeting slots through this Calendly link. And please mind, like all the communication with me or whatever I want to share with you will happen through only Slack. So we'll not be sharing any communication over emails. So I will strongly advise you or request you to please do join this Slack channel. Okay, so after completing all the formalities, let us go to our main agenda that is part of our today's lecture and future training. So what is VLSI and what are semiconductors? So VLSI is the full form of VLSI is very large scale integration, and it refers to a technology or electronics technology where thousands or millions or nowadays even billions of transistors can be integrated into a single chip. So as you can see on the right hand side of my slide, so this semiconductors basically evolved like in 1950s mostly. So from that time period, there has been revolutionary changes in semiconductor technology. So we started with SSI, LSI, VLSI, ULSI. So during that time period, people used to give these different terminologies based on how many number of transistors can be integrated on a silicon area. So accordingly, VLSI was like it was originated, but after a certain period when people thought like this number of transistors which are getting integrated on silicon is increasing exponentially, so they stopped giving further nomenclature. But that's where this terminology got famous, this VLSI, that is very large scale integration. And you can basically, at that time, it meant like 20,000 to maybe 1 million kind of transistors, if they can be integrated into a silicon area. That technology was called VLSI, but it has now kind of become of a generic name to IC design or IC technology. And why do we need such a large scale of integration? That is because we want to create more complex and very high efficient and high performance electrical circuits, electronic circuits or electrical circuit. Because building these kind of circuits using discrete electronics is challenging, and it does not serve, it serves only a limited purpose. You cannot achieve too much using making any fundamental electronic circuit using discrete parts like a separate resistor, capacitor, inductor, anything. So that's why this technology involved where on a single substrate or on a monolithic substrate like a silicon or a germanium, you can integrate multiple transistors or multiple components on it. So that's how this VLSI terminology came into picture and now became popular. But so one thing is like for VLSI, we need semiconductor. VLSI cannot be done on a PCB or any discrete substrate, other than a semiconductor. So for that, we need to understand what is semiconductor. So semiconductors are basically class of material. Generally, we know only about conductors or insulators. That is material which pass the current, allow current pass through them, or which block the current. But semiconductors lies in between them. So the property of semiconductor is like we can control their conductivity, the amount of current, how much current can flow through them. We can either control the amount of that current, or we can entirely turn off that current or allow the current to pass. That is, we can make it act as a switch. So that is a property of semiconductor that has basically revolutionized the whole electronics industry, because that gave the leverage to engineers and scientists to put lot of number of transistors or other integrated devices on silicon material, and hence gave the rise to this wonderful semiconductor industry and VLSI technology. And some of the popular class of semiconductor materials are silicon, that is the most popular one. And there are some compound semiconductor materials like gallium arsenide and silicon carbide. So these are specific materials. Just like for conductor, we talk about copper, iron, silver, other things. These are metals and they fall in the class of conductors. Or for insulator, we talk about like wood, soil, etc., etc. Similarly, for semiconductors, they are specialized class of materials, which are mentioned in the second point. And why the semiconductors are important? Because they allow us to create all the wonderful basic fundamental elements which are required for building electronic circuits like transistors, diodes, resistors, capacitor, integrator. All these primitive electrical elements, they can be put on the silicon die. So I hope everybody is able to see my slides because I am getting message in chat like some can't see my slides. Can you please anybody confirm? Are you able to see my slides?
Yes, actually, I can see it very clear.
Okay, no problem. I will continue then because some of the people are complaining like they can't see my slides. So I think it's not an issue overall. Okay, I will continue then. Okay, so we talked about VLSI technology, we talked about semiconductors, and now we talk about what is the relationship between VLSI and semiconductor. So basically, semiconductors are foundation over which a VLSI technology can be applied or implemented. Because as I told you, VLSI means you are integrating 20,000, 20K to maybe 1 billion components on a small piece or area of silicon. So that obviously that cannot be done on any other substrate like a PCB or any other inert substrate. For that, you need a semiconductor material, and that it can be silicon, gallium arsenide, silicon carbide, gallium nitride, other similar this kind of material. So these are semiconductor material which are foundational for building VLSI circuits. And obviously, VLSI basically uses the properties of semiconductors. That is how the current can be controlled over a semiconductor material, or how it can be used as a basically an amplifying element or a switch. So all those properties allow us to integrate multiple circuits on a semiconductor material, and that basically uh, allows us to implement the VLSI technology and also achieve high density, high performance electronics. Okay, and what happens with the combination of VLSI semiconductor is like there is a lot of advancement. So I think I need not uh, repeat myself about it, but everybody is seeing the fruits of how much benefit we are getting from semiconductors and this VLSI technology. So over the years, we like all the gadgets we are using, mobile phone in our hand or the laptop which through which I am communicating with you. All these are wonderful examples of semiconductors. So I think right now we cannot imagine basically humanity in our current form if we do not have this wonderful gift of semiconductors with us. And what are those applications which I'm talking about are different modern electronic devices, everything like household items which we are using, like laptops, or even our like goods which we are used for our daily life, like refrigerators, ACs, air conditioners, everything uses semiconductors. And it doesn't only allow us to use in our day-to-day life, but all the other things like all the big strategic items like airplanes, missiles, everything, and the communication 5G, 6G. You talk about anything, everything depends on semiconductors. And the VLSI is that technology which enables people or designer engineers to implement what different kind of circuits or as per the requirements on the semiconductor material. So overall, what I want to emphasize is like semiconductors are a base, the material which are used, and VLSI is that technology which allows people or engineers like us to implement our ideas or our circuits, what kind of the analog, digital, RF, whatever we want to implement on semiconductor materials. Okay, so I am emphasizing again and again about VLSI, but we in order to understand the importance of VLSI, first we need to understand like what is the alternative, what was the alternative to that? That is discrete electronics. So there are two options. You can build a similar circuit which you can build on a silicon, but if you want to build it on a PCB, that will occupy lot. It will make lot of complexity. The area which will be required, the number of component, discrete component, number of integrated circuit, individual integrated circuits of passive devices, these will be huge, as can be seen in this bottom example. This is just for a reference. So this is an example of how a PCB will look like if you want to build and this is what a silicon looks like. So this could, for example, let me just give you, and this area could be just a 5 mm by 5 mm area, a die, silicon die, and you can put so many elements on that silicon die. And this might be a size of just your thumbnail. And then this PCB can be anywhere around like maybe 10 centimeter or maybe 20 is half a meter around area. So you can just imagine like if you want to build a mobile phone using a PCB, is that even possible in today's world? No. So obviously you cannot use such big PCBs to make miniaturized electronic devices, which we are nowadays using. For that, you obviously need VLSI circuit. So these are on the left side, I have compared what are the benefits. So the integration is very high in VLSI circuits or ICs. And then size and compactness, I gave you an example, like whatever you can, the area which is required for realizing any IC or VLSI circuit is is minuscule as compared to a discrete PCB circuit. And performance of electronic circuits are also, VLSI or ICs are also very high. I think you all must be hearing about like how much in demand are nowadays NVIDIA GPUs. And why is the demand for that? Because they are very high performance integrated circuits. So you cannot match a performance which can be achieved in IC with compared to discrete circuits. Maybe in some domain that thing is not true. Maybe, for example, in case of high power electronics. For example, if you want to build some kind of a DC-DC or AC to DC converters for electrical vehicles or some for power machinery, so there you might still require to use some discrete semiconductor devices along with some other passive elements to build your circuits. But for all the other requirements, like for computing or memory or for communication, I think ICs and VLSI is sufficient enough to handle those needs. And although manufacturing process of VLSI circuits is very complex, so I think you must be knowing, like putting up a silicon foundry is not a joke. The amount of money which it involves, the amount of technology and skill level it involves is like very high grade. You cannot compare it with any other manufacturing process on our planet. The manufacturing of silicon or VLSI circuits or ICs are very complicated, and the setting up a foundry can cost you anywhere between maybe $2 to $3 billion to somewhere around $20 billion. But putting up a PCB plant or like manufacturing PCB is still cheap. So obviously cost of silicon or ICs are very cost manufacturing, but still the advantage which the IC technology gives anytime outweighs the benefits which are given by PCBs. Similarly, applications. So I think I have just now told you about like what kind of application ICs are used in. So all the electronics, the modern day electronic gadgets which we use, all require IC technology or VLSI technology. Okay, so this slide covers you basically about a microelectronics domain. So what is microelectronics and how is it different from discrete electronics? So electronics is in itself a very vast subject, and there are different kind of fields in it. And microelectronics refers to the field where the components which are laid out or which are used for design of circuits or manufacturing are in like very small scale, in micrometer or nanometer scale. So that's domain of microelectronics consists of two kind of substrates. So there is an inert substrate and there is an active substrate. So inert substrate can be which is not a semiconductor material. It can be an insulator substrate like a glass or a sapphire, over which some layers are deposited, and using those layers some kind of structures are built, and those are used for building some microelectronics circuits. But that is a small area. So the main area of interest in microelectronics is active substrate, and active substrates are of different types. As I told you in previous slide, it can be a silicon, germanium, or some compound semiconductor materials like gallium arsenide, gallium nitride. But since we are talking about VLSI and we want to discuss about the most abundant material used for manufacturing or realization of electronic, so that is silicon. So I think more than 90 to 95% of all the manufacturing which happens in integrated circuit technologies happens on silicon substrate. And in silicon also, so transistors can also be of different types. For example, there are MOSFETs, there are bipolar junction transistor, BJTs, then there are MESFET. Again, in gallium arsenide, they are HEMT kind of devices. So transistors are of different nature based on their architecture, like how the current is controlled through them using gate and drain and substrate structures. But the most used transistor is MOSFET, and that too on silicon technology. And in MOSFET also, there are two type of MOSFETs. There is NMOS and PMOS. And then there is a technology where by NMOS means like all the circuits which are built on IC are built only using NMOS transistors. Or if it is a PMOS technology, then only PMOS is used to build kind of circuits. But the most prominent or most used technology right now in the world is CMOS. So CMOS means complementary metal oxide semiconductor. That is, both NMOS and PMOS transistors are used on a same substrate to build variety of circuits, both analog, digital, RF, whatever you want to build. So that's why I have highlighted these blocks here. So in the field of microelectronics, the most obviously used substrate is active substrate, and that too it is silicon. And inside silicon, the type of transistor which are used is MOSFETs. Although bipolar is also available in silicon and it has its own benefits, but those benefits are limited to some specific areas in very high speed electronics, or in kind of where you need high gain properties, or where you need a low noise amplifier performances. So those are the areas which require uses bipolar transistor. But apart from that, most of the circuits right now which are built, and especially in digital designs, are built using MOSFETs. And now even MOSFETs are getting relegated back at very high-end nodes, like less than 22 nanometer. Below 22 nanometer, there is a new class of transistor which has come up that is called FinFET. And now another type of transistors are being coming up in foundries that is called GAFET, that is gate all around field effect transistor, GAFET. So these kind of developments keep on happening in semiconductor industry. But still, for our purpose or for analog design, I think silicon technology and using MOSFET transistor are still the workhorse of our field.
So Vipul, if you allow me here, if you have any issues with the screen, you can't see the slides, just use the browser instead of the application. So just use the browser, and then you can see the slides. Sorry again, Vipul. Please continue.
No problem. Dr. Sharma, should we wait for 5 minutes so that people can set up it on browser? Maybe we can pause for 5 minutes and then start.
Sure, we can start for 5 minutes. Yeah, sure.
Okay, so I will wait for 5 minutes. You please set up your browsers, and then maybe we can start after 5 minutes.
Welcome again into the first lecture of this training program. So, Engineer Vipul, you can continue your lecture.
Okay, thank you, Dr. Salman. I will continue. So, okay, so we saw in this slide, like, what are the different materials and different kind of transistor which are used for semiconductor electronics field, which is called microelectronics, because we are dealing in scales of micrometer and nanometer. Okay, now let's move to next slide. So now, in order to do a design of a circuit, any circuit, we need to follow a proper structured approach. So there are various steps involved in any design cycle. Here I'm specifically talking about analog IC design. If you need to design a digital circuit or a RFIC circuit, so approach remains similar, but the steps might be different, because the starting point for digital design is different. There you are using codings, basically Verilog and VHDL, and from there you need to build your layouts and tape out your design. And analog IC, the approach is which I will be explaining next. So these are the various steps, design, concept. I will be explaining each of these in next slides. So first we try to do electrical design. By electrical design, I mean, like, you need to have some specific architecture to achieve some functionality, whatever functionality you want to achieve. If you are building an amplifier, you are building a filter, whatever circuit you are building kind of a transmitter, receiver, or a complete complex digital microprocessor, whatever that circuit is. First, you need to implement that circuit electrically. That is, what kind of components you need to be used in that circuit, and what will that architecture looks like. Now, once you have finalized the architecture, you need to simulate it, and then that completes your electrical design cycles. Then comes the physical design. That is, whatever electrical components you have started, you need to realize them on a silicon wafer or silicon substrate. For that, you need to build a layout of that circuit. and it involves some verification steps. So once these electrical and physical design steps are completed and your design is okay, you send it for fabrication to a foundry. That foundry means like you must have heard about big foundry names like TSMC, Intel, Samsung. So these are the places where whatever circuits you build based on the technology provided by those foundries, you get your designs fabricated. And once the fabrication is complete, then comes next step, that is assembly, packaging, testing. You need to basically convert your silicon wafer into a final packaged IC, which is what is finally used in implementing any product. So that cycle is completed in a specialized unit called ATMP plant. ATMP, the full form of ATMP is assembly, testing, marking, and packaging. So all these activities happens there. And once that is done, then comes the testing and verification step. And once it is done, our product goes into final, like wherever it needs to be used, whether it is to be used inside a mobile phone or a laptop or like a car. So that's a product where that IC will go on. So in this particular training, which we will be following next 1 week, we will be emphasizing on this step. Like once we have done the design, fabrication is done, and it comes back to us, how do we test it? What kind of signals we need to apply to what kind of a circuit, and how to see the waveforms of those circuits. So these are some of the steps which we will be trying to learn in this training program. So the focus of this program is on this testing part. Okay, so now let us go through one by one all these steps which I covered in this slide. So the front-end design or the electrical design starts with a design concept. So obviously, if you want to design something, first you should have an idea like what kind of circuit you want to build. So that demand can come up from like, for example, if you're working in a big semiconductor design company, fabless design house, your company might be building a state-of-the-art, like maybe let us say you're working on a 6G, developing a new circuit for a 6G technology, which is yet to be coming up. So that is a concept. You should have some idea. Once that concept is clear, like you are building a chip for 6G, then you need to define the specifications. You cannot start blindly. You have some references available from your previous designs like 5G, 4G technology. And then there are some global agencies available in the world, like ITU is one of them, which define the specifications for whatever technologies are used in world. From there, you get an idea like these are the specifications for which I need to design my circuit. Once all those things are clear, then you decide on like which is the technology or which is the foundry in which I want to design my or build my circuit. And then you take a PDK from them, that foundry, you contact that foundry, you get an access to their PDK and start building your design. That is, you start implementing it in form of a schematic. Based on whatever architecture it has been selected for your circuit. So you implement it as a schematic. Once schematic is built, then comes the next part, that is simulation. So you need to validate your design, like whatever circuit or whatever architecture I have chosen and whatever are my target specification, are they meeting or not? And that can be realized using simulation step. So these are the phases of your electrical design steps, where you start from a concept and then end it with simulation stage, where you finalize your electrical design. Like this is my architecture, these are my components, these are the sizes of those components, everything is finalized. So this completes the electrical design, or what we also call sometimes a front-end design part of a IC. Now comes the back-end design or physical design. So now whatever things we have done in electrical design are all in virtual domain. By virtual, I mean like it is all done in simulator. You are using a simulator to build your circuit and also simulate it. So there is ultimately we want to put our circuit on a silicon. It has to be physically realized on some substrate. For that, we need to convert our electrical design into a layout. So whatever components which we have used in our electrical design, in our schematic, they have to be converted into their equivalent layout. Like whatever transistors are used, MOSFETs are used, whatever resistor, capacitor, they are replaced with their layout elements. And then those layout elements are placed in layout tool. There are specialized EDA tools used for these activities. And then the connections are made between those. It is something similar to like if somebody is from PCB background, you select your components and then assemble those components or solder those components on a PCB, and then there are tracks in between to connect those components. So similarly, in case of IC also, all these activities are covered in a IC layout domain. That is where you place all your components from your schematic and try to make the connection. But one critical thing about ICs are very complicated. As I covered in my one of the earlier slides, VLSI means you are using maybe 20,000 to 1 million transistors in your design, and these are only transistors. Apart from these, there will be passive elements like resistor, capacitor, etc. So you can understand like the count is in millions. So it's very difficult to like in PCB, there are limited number of components you can keep track of those, and if even if there are some misplacement or solder, they can be visually checked. But in case of IC, it's not possible. So what needs to be done is like whatever layout you have done, you have to check whether this layout is what electrically is similar to my schematic, like whatever elements are used in my schematic and how they are placed, how they are connected, are those protocols similarly followed in my layout? For that, LVS is required. So what is LVS? LVS is layout versus schematic. Basically, you check your layout whether it is electrically exactly similar to your schematic. Like there is no mismatch between them. Because if there is some issue, obviously whatever you are trying to implement on silicon will not work. Whether there might be some electrical connection which is open or something is shorted out, so that will not work. So that has to be ensured, and these are part of a physical verification activities, that is LVS. And what is DRC? DRC is like, since we are talking about IC technology, microelectronics, and all the components which are placed are in micrometer domains, very small. And if they are placed in a very small area and placed very nearby to each other, there can be several issues caused in manufacturing. Like the foundry has its own processes and recipes to build those components or those layers on a silicon wafer. So they basically have limitation which can be from the process point of view, or there can be from a recipe point of view, or from even from a tool point of view, because tool might have a limitation to etch two layers or two structures very nearby to each other. So all those limitations are informed design rules. So foundry basically places some restrictions on these layers, like these layers cannot be nearer to each other than this minimum distance, or this layer should not overlap this one, or there are several such rules available. These are called design rule checks, and a foundry provides these rules as part of a PDK, and it is a responsibility of a designer that he needs to ensure like whatever layout he is building, it basically passes those DRC checks. That is very critical, because if your layout is not DRC clean, foundry will not accept it for fabrication. So that these are two critical verification checks which needs to be performed on layout. And the last one is parasitic extraction, because whenever you are doing simulation in a schematic domain, there are no metal lines available, so all the interconnects are ideal. But when you basically convert that schematic into a layout, you place actual metal lines, and that lines can be maybe very long or very thin, based on the placement of the components in your layout. And then obviously, when a metal is placed between two components or regions in your layout, it will introduce some parasitic resistance, capacitance, or inductance elements. So those elements needs to be evaluated, and then effect of those elements needs to be basically annotated back on your schematic, and then verified whether due to presence of those parasitic, is your design being hampered in some way, are your specifications getting affected. So that is a part of parasitic extraction and post layout simulation. So once that is done, your design is ready to be sent for fabrication. So what is done in what do I mean by getting ready to be sent for fabrication is whatever IC layout you have done, it is passing all your verification check. You convert it into a industry standard format that is called GDS2 file. That is a standard format file which can be simply converted from your IC layout to GDS2 file, and then that file is sent to to mass manufacturing. So I think you must be knowing how manufacturing happens in foundry. Inside a foundry, there's a wafer, and over that wafer, different layers are imprinted using light source. and there is a photomask in between through which a light is basically focused on a wafer surface, and those photomasks are basically generated from your IC layout layers, and for that you need a GDS25, and then a photomask manufacturing takes place at a separate unit, and then those photomasks are used inside a foundry for doing actual IC fabrication. So IC fabrication, I think in itself is a vast field and a complex domain, but as a like a design engineer or test engineer, that is not under your scope, because there are specialized like factories for handling those steps, and there are specialized engineers and process engineers and fab engineers who take care of all those steps. Okay, so once fabrication is done, the next step is to under fabrication. The fabrication happens on a complete wafer. So that wafer can be a 200 diameter big or a 300 diameter big. From that wafer, you need to extract the dies, and those dies now need to be assembled inside a package, and then bonding needs to be done, and packaging and the lid has to be put on the top of that package, and then a final package is done, and that is ready then to be tested, and then after verification to be used inside a product. So that is actually a whole complete life cycle of a IC, how it basically propagates from the design stage or concept stage to the final product. Okay, so this slide again repeats all those steps which I covered in last few slides. And now these are the first two are the basically stages of IC design, where we do IC design. There are big semiconductor design companies in the world, like Qualcomm, Broadcom. You must all have heard about Apple. Is also now a semiconductor IC design company. So these are the companies which follow these steps, all the IC design steps. These are basically analog IC design steps. Similarly, there are steps for digital IC design, and they do all the IC designing phase of the semiconductor VLSI circuit or IC. Once that is done, it is handed over to foundry or a fab, which does all the manufacturing. Once a foundry outputs its end product in form of a complete fabricated wafer, that wafer is handed over to a ATMP plant, and then that ATMP plant does all these post fabrication steps, that is of assembly, packaging, testing, verification, and then final product is released. And the full form of ATMP, I think I mentioned earlier, is assembly, testing, marking, and packaging. So these are separate units. So these are three. If anybody is thinking from a career point of view, these are the different domains. One is an IC design domain, another is a fabrication domain, and third is the ATMP domain. And in these domain itself, there are like sub career options. Like in IC design, there is like front-end design stage where a designer does schematic and simulation steps. Then there is a back-end design stage where a designer does IC layout, and then there is a verification engineer who only do verification. Similarly, inside of fabrication, there are different steps followed inside of fabrication, like lithography, etching, deposition, diffusion. So each of those steps have their specialized engineers. So again, those are separate career options inside of foundry. Similarly, in ATMP, there are assembly and packaging engineers take care of all the assembly, packaging, bonding requirements, and then there are test engineers. This is the focus of our current training. So these are, again, there are different career options in ATMP. So I think if anybody is interested in really making their career in semiconductor domain, which is again like very demand nowadays, you must be hearing how much investment all the governments are making in it. So there are very different kind of options available for you to explore. Okay, so this is a visual representation of whatever I mentioned in earlier. So this is how a wafer comes out of a foundry. This is a complete wafer. Now this wafer is cut and diced so that different like multiple dies are extracted from this wafer. There are specialized machines, diamond cutters, used to extract those dies. Once that die is extracted from a wafer, it is placed inside a cavity of a package. So this is a dip package. This is a cavity, and this small black is a die. So this die is placed inside this package. So once a die is placed, now the electrical, you must have seen a package has some pins, metal pins around it. So those pins are connected to the IO pads of this die. So those connections are made through these bond wires. So these bond wires you must be seeing, these are small bond wires. These are generally made of copper or gold also. These are aluminum also. So these are the materials used to make those uh, bond wires. So once the bonding is done, now the top of or the lid of this package has to be closed. So this step is called encapsulation. So this is what I was talking about ATMP. So these all steps are done inside a ATMP unit. And once encapsulation is done, the final package IC is ready. Now this package IC is further sent for testing. And once it is validated, it can be used inside a product. Okay, so this was all about the life cycle of an IC, like how we follow different steps to mature it. Now let us talk of some little bit about the intricacies of a technology, CMOS technology, which is ultimately used for building an IC, and then that IC is which we'll be using for our testing in coming lectures and like the online or the remote testing sessions. So in our case, the IC which we have designed is using Skywater 130 nanometer technology. So this is a US based foundry, and 130 nanometer technology is like 5 nanometer 130. This is a channel length of a transistor. So this is a transistor, this is an NMOS transistor, and this is the drain area, this is the source area, and this is the gate. So whenever you talk about a technology node, like we say this is 180 nanometer, this is 130, this is 22 nanometer. So this is the dimension which we are talking about, the channel length of a transistor, smallest channel length possible to be fabricated for a transistor in any technology. So we basically refer to any technology by its node, and this is what represents it, the minimum channel length possible for a transistor in a particular technology. So in this technology, the minimum channel length possible is 130 nanometer. So why this factor is critical? Because it controls several performance metrics of a transistor. It controls like how fast your transistor will work and how much gain, other properties it can affect. So all those properties of a transistor are affected by its channel length. And for any circuit or any active circuit, VLSI circuit, transistor is an engine of that. Just like for any automobile or any vehicle or bus or truck, you talk about the engine is a powerhouse. It drives that vehicle. Similarly, for any electronic circuit or a IC, the transistor, how good your transistor is, how powerful it is, it drives the performance of that transistor. So that's why it is a critical element. And every time whenever we talk about any CMOS technology, we refer to it by its channel length. So in our case, why Skywater 130 nanometer is important? Because this is an open source. So one thing about IC or semiconductor is like it is a very closely guarded technology. Nobody wants to share their knowledge with each other. You have to like follow various legal basically what can you say NDA requirements to get access to any foundry's technology, their PDK. But Skywater and 130 nanometer is the first one in the world which have made all this information available in the public domain. And that's what we have tried to build, tried to use for building our circuit using the open source PDK of Skywater 130 nanometer and also the tool sets which are available for this particular technology. So this is all the information about Skywater 130 nanometer, because the circuits which we will be using for testing in upcoming lectures are built using this technology only. Okay, so in any fabrication technology or an IC technology, there are two type of fabrication layers available. One is called back-end layers and the other is called front-end layer. So the back-end layers are the metal layers which are used for making the connection between different components on a IC. So as I told you, there could be like hundreds, thousands, or millions of components on a in a VLSI circuit. So in order to make connections, you cannot make connection using a single layer because this is so complex. Like layout is very complex. So many components are laid out on a die area. You cannot make connection using one because everything will get shorted out. So therefore, you need to use multiple layers. So in case of sky water 130 nanometer, there are 6 metal layers. So 5 are aluminum layers, and the lowest one, that is called local interconnect, is a titanium nitride layer. So these are the 6 metal layers which are used. The purpose of these layers are to make the connection between different elements in your layout, and also to build a passive component called MIM capacitors. So a capacitor can be built using 2 conductive layers in this stack. So this is one property of this Skywater 130 nanometer. These are the backend layers of this technology. And then these are the front end layers. So the backend layers are used for making interconnections and all other passive elements like capacitor. And these are the front end layers. These are the actual active layers which are getting built inside the surface of a silicon wafer. So there you do topping and other implant kind of steps which are followed inside a foundry to build different regions of a transistor like drain area, source area, and also build wells, everything, etc. So this is a basic structure how a typical front end layers of any CMOS technology looks like. So this is a P substrate, a silicon wafer, on which you will start building your layers to implement transistor. Then there is a deep N well, which is used to make P well, and then there's N well, which is used to make NMOS transistors, and then these are other diffusion areas for building drain source and bulk connections. And this is the poly layer for building the gate connection. And these are the local interconnect layers which are used to connect different transistors or the element, which I discussed about here. So this is just a brief overview about how like a cross section of wafer looks like if you try to cut wafer from its cross section. So these are the different layers which are seen or built inside it. Okay, so just to basically make you aware, you cannot view these things by naked eye. You need to use very high like resolution microscopes inside a foundry in a closed protected environment where no dust particles are there to view all these layers. But this is how the structure looks like. Okay, so we talked about like what steps needs to be followed to build our circuits, what happens inside a foundry at assembly, testing, marking, packaging. But since we are interested in knowing like how this design is done, actually how a designer implements his ideas, what are the tools used. So in electronics industry, there is a common word used for all the softwares used, that is called EDA, electronic design automation. These are special set of softwares which are used for building electronic circuits. But inside EDA also there is a class of software which is specifically used for IC design. So EDA is used for every kind of software. Like even if you are trying to build an antenna or let us say PCB design, for the software used for those are also called EDA. But for IC design, there are sophisticated softwares and they are very like resource intensive and also need some specialized learning to understand them, how they work, and what are the steps need to be followed in design cycle, which tool needs to be used in which step. So these are specialized software specifically used for IC design. And the critical thing is like whatever stuff which we are seeing, we are using in our daily lives, or the laptop which you are using to view this lecture, or mobile phone, anything cannot be possible if these EDA software would not have been there, because these are the software which enable designer to implement his idea on silicon. And as I mentioned, I think repeating it again, the number of components involved are in millions and billions, so it's not possible to do it by manually. Obviously, you need to automate the complete IC design process, and that's where these design softwares play a critical role, and they save a lot of time. Because manually, earlier people used to do, like maybe 5 or 6 decades back, people used to do this thing manually also, but then the complexity was very less. They were dealing with maybe few transistors, 10 or 20 maximum components, so that can be handled manually also. But once the number of components exploded, it's no longer possible to do in a time efficient way using manual steps. So the use of EDA can be divided into 4 crucial steps. That is to design. Basically, design means like doing the schematic design, building the schematic of your circuits, then to simulate it, verify it, how the like performance of that circuit, and the value verification, like build the layout and verify all the layers and all the requirements from the foundry point of view. So those verification steps are required, and then the manufacturing. So in order to do the manufacturing, you need to build a layout and generate a GDS. And also for mask data preparation and all those critical steps, also a separate set of EDA tools are required. So the point to ponder here is like EDA is a very crucial part of semiconductor industry and IC development cycle. Without it, like I think nothing would have been possible. So generally, it remains in background, but it is a very essential part of our modern semiconductor industry. And also, again, from a career point of view, there are a lot of scopes in Indian industry also. So you must have heard about big EDA players like Cadence, Synopsys, Mentor Graphics. So they do also have a good requirement of people who are from semiconductor domain, like who understand device physics or circuit electronics or the performance of the various components used in IC design. So people with that background are generally in very high demand in these kind of EDA players, big EDA players. Okay, so as I talked about, we need different kind of EDA softwares at different stages of IC design. So in our case, we had used open source PDK from Skywater 130 nanometer, and similarly we use open source toolchain also to build those circuits, which we will be testing in coming weeks. So for schematic design, like to build an architecture of a circuit, like how to place the components, the tool uses Xscheme. For building a layout, a tool called Magic is used. For doing DRC, design rule check, provided by the foundry to to calculate or measure that spacing between different layers and their placement. Again, Magic is used. For LVS, layout versus schematic, NetGen is used. Parasitic extraction can be done Magic and IC tapeout. Also, these are different tools, EDA softwares, which are used in our open source design flow to building our circuits. Similarly, if you are using EDA flow from Cadence or maybe Synopsys or Mentor Graphics, so each of those vendors have their own tool chain. They have each of these steps can be performed by a separate software in their own EDA design flow. And I think I have covered maybe there are a few training sessions or workshop I have already conducted in previous sessions with SSP, where I have extensively talked about these tools and how to use them. Okay, so once we have done a design, and send it for fabrication. So one critical thing to know about is like fabricating a design or your idea on a silicon is not a very cheap process. It is a very uh, basically costly process. So whenever you are building a new design which is not validated, like let us say you're doing it for a first time, so it's you do not want to risk so that much of a cost. So for example, if we talk about maybe technology node like 130 nanometer or 180 nanometer, so that the cost of mask or fabricating a single wafer can easily go around the cost of $1 million, $1 to $2 million. So you can just imagine like how costly this is. Not everybody cannot afford it. But if it is just an idea, like you are trying something, you are prototyping something, you do not want to spend or risk that much amount of money to just try your idea. So the way to do is like multi-product wafer. So what happens in multi-product wafer, like if you are just trying to build a prototype, you want to share the space on that wafer, maybe with some other customer who is also doing a prototype. And then there can be several such customers which can be accommodated on a silicon area, wafer area, and whatever manufacturing and masking cost is involved, that can be basically shared between them. That way, the cost of basically prototyping your design gets reduced drastically. So that is what approach is generally used if you are trying to prototype or you are trying to basically learn something. Maybe some universities or colleges, they do use prototyping vehicle, MPW shuttle services to implement their ideas. So that is one approach. Once your design is validated, or like in MPW, you did your design, you got it back, you tested your design, and you are happy, like my performance is meeting as expectation, and now you want to give a bulk order. For example, whenever you are building an IC, that IC might have demand in millions, like maybe some customer is telling I need 10 million ICs of particular design. So how to do that? Now once your design is validated, you give a bulk order to a foundry. Like you will tell foundry, like I want to place an order for so many ICs, so you run my complete lot. The whole wafer should contain of my design only. So a foundry will run a dedicated wafer lot for your design. So that complete wafer and all the wafers in that lot will be used by you. But in multi-product wafer, you are basically sharing that space, and obviously cost is getting reduced with other customers on that shuttle service. So what are the benefits? So multi-product wafer, basically multiple customers are using that space and their designs are available on a single mask. But in a dedicated wafer, a single customer is using that mask. And in multi-product wafer, since you are sharing your masks with other customers, so there's, in case if something goes wrong, there is no scope available for customization. It is very little available. So in that case, you might need to send a complete new design for in a next MPW shuttle for fabrication. But in dedicated wafer lot, there is some control or customization available to customer. So that he can, for example, if he needs some tweaking in his design, he can implement it by changing only single mask in his design. So that kind of customization is available. But the benefit of multi-product wafer, it is very cost effective. And so that is why it is mostly used by small customers or universities or startup kind of entities. But dedicated wafer lot is obviously it is very costly. But then obviously when if a person is giving an order for dedicated order, so he must be having order from his customer for those kind of quantities. So that's why it is used for bulk wafers or bulk production. So idea of putting up this slide and sharing with you is like our designer should have a feel of these kind of activities. Like these are commercial activities involved in taking the decision, like in what if he is doing some new design, how he would like to get it fabricated, what kind of cost he is ready to put on the success of that design. So these decisions are also sometimes critical in designers day-to-day working. Okay, so in our case, the whatever designs which we are using for fabrication and which we'll be testing, we have used a shuttle called Chip Ignite. So in our this shuttle is being run by a company called eFabless in this Skywater 130 nanometer foundry. And here also a single mask is being shared with by multiple customers. As you can see, as an example, this designs from multiple customers are put on this mask and they will get fabricated together. So this is what I was referring to in my previous slide. And in by also the eFabless provides you with a Caravan IC development business model where they have a predefined structure of an IC in which whatever design which we got fabricated from this shuttle, that design is basically put inside this harness area and then gets fabricated. And after fabricating, a test board gets delivered to a customer. So this is because we are trying to do a prototype kind of an activity. So that's why they have made it easy for a person or anybody who wants to basically try their ideas. They want to design something and then finally they get this kind of a test board. But if you are working with any professional company or any professional setup, so there you do not get this kind of a liberty. There you need to do all these activities on your own. You need to talk to like a test team. They will make a test plan for you. Accordingly, a test board needs to be built. And also the kind of package needs to be selected. All those decisions need to be taken by a designer, obviously in collaboration with other teams like the testing engineer or package engineer. So all these activities becomes basically very cumbersome decisions to be taken. But here, this company or this setup provides us this kind of a liberty where we can just simply put our design here. We can get it fabricated, and then every step like testing, oh sorry, assembly and packaging is taken care by them. They provide a QFN package, and that package gets soldered on this test board, and we can directly use the pins available on this test board for testing our designs, which we got integrated in this empty area. So this is the approach which we will be using. We already have this test board with us, and this the chip on mounted on that test board has the designs, the 4 analog designs which I covered in earlier slides, and we will be testing those designs using this test board. And I think the last few slides covered what kind of designs are available. So this is a die area which was designed by us, and these are the different kind of designs available. This is a single stage amplifier design. This is an operational amplifier, bandgap reference, and ring oscillator. So these all designs are placed in different locations on this layout as per the availability of pads nearer to them. And then there are some silicon test structures also put on this die, but they cannot be measured on a package level. For measuring them, we need to do on wafer probing, but that is not under the scope of this training, but just for your information. So what we will be concentrating right now in this training is to test these 4 analog circuits. So this is what we will be covering, how to basically analyze this circuit. I will share some information about these circuits in next few lectures, and also basically check like how we can basically do measurement on these circuits actually on a test board and using a dedicated measurement equipment, which I will talk about in upcoming lectures. And this is the actual die for picture of a die, silicon die, which we took using a high resolution camera. And this is the picture of this area, this layout. This is the layout which was done in Magic, and this is actual silicon die. The silicon die actually assembled inside this package, QFN package, and this package is mounted on this test board. And these are the different pins available on the periphery of this test board. Using these pins, we will apply our test signals, input signals, power supplies, and there are also IO pads, output pads on here available, output pins available from where we can see the output signals of the various circuits, these 4 circuits mentioned here. So I think this is all about our this kickoff lecture. I think I had give you an idea like what we are expecting to come in our upcoming lectures, how we plan to test the circuits available inside this chip and on this test board. So all these things we will be covering from tomorrow onwards. So I think that's all from my side. If anybody has any queries, they can put their question and answer in Q&A box. So we have some time, we can quickly discuss those queries.
Thank you so much. So as our engineer said, if you have any question, you can just write it, and he can answer it.
And I have also shared a link on a chat in this lecture, through which you can please fill a form to join the Slack. You can fill the information required there. I will send you the invitation to join a Slack, and from there, I will be putting all the slides of the lectures and recordings whenever they are available. So please make it a point to join the Slack so that you can get up to date on whatever activities are happening and whatever content I am sharing there. So please try to join this link. I will once again share it on chat box for your convenience. Once you join a Slack, you can also put your queries there. We can have a discussion there in one where, because there we can put contact. You can contact me anytime.
Okay. Thank you again, people. Thank you for your attendance. And tomorrow we will meet at 2 p.m. Thank you so much. Have a good day.
Okay, thank you, Dr. Salman, and have a nice day, everyone. Bye. Okay, good. Okay, so today's lecture, that is lecture number 2 in our series of how to test VLSI circuits, is on introduction to the first of our blocks in our chip, that is common source amplifier. So yesterday I discuss about like what is basically VLSI design, what are semiconductors, how are they related, and all the basically steps involved in design of ICs and VLSI circuits, and all the requirements after that, like how the IC goes to fabrication and then it's come back, then it goes to an ATMP unit for testing, assembly, packaging, and then finally it is ready when in the package form. Then how would you test it? So that is our main at the end of this training. And today we will start with our first circuit, which is available with us. It is fabricated in Skywater 130 nanometer technology, and we will start testing this circuit in from next week whenever the slots are open. You can book your slots and decide whichever circuit you want to test out of the four which we will be discussing. So yesterday we talked about basics, introduction. Now today we will talk about common source amplifier. What is common source amplifier? What is its significance? And how we can test it, and what is the equipment which will be used to test it. So all these aspects we will see today, and later on we will look on to remaining three circuits. So common source amplifier is basically a fundamental amplifying stage used in any analog integrated circuit. So obviously an amplifier requires an active device, active element. So in this case, since we are talking about CMOS technology, so that active element is a NMOS transistor, or it can be a PMOS transistor also, but generally we use NMOS transistor. And this is a basic stage we used to build more complex circuits. So there are two more fundamental single stage amplifying stages. Such similar to common source amplifier, there is a common drain amplifier, common gate amplifier. So they have their own applications in analog circuits. But the main function of common source amplifier are following. These are the high voltage gain, because it gives you around more than 10 to 15 dB of gain. And based on the application or requirement, you can also try to enhance it using cascade or other stages. But that is a fundamental application. Wherever you want a gain in your application, in your signal chain, a common source amplifier plays a role in one or another way. And it is versatile, so it can be used in different kind of applications. If you want to build amplifiers, specifically audio amplifiers or operational amplifiers or sensor circuits, so these are various applications where this kind of a single stage common source amplifier is used. And also the multiple stage designs. For example, if you have a stage where you want enhancement in your gain, so you can anytime apply a common source amplifier after that stage, cascade it to the existing stage and try to enhance the gain. Obviously, there are some other aspects which needs to be taken care of while designing such circuits, like feedback, stability, etc. But then common source amplifier, one of the fundamental stages which is used for enhancing the gain of any signal chain. And another property of common source amplifier is like it has an high input impedance, and that why that is because we are using a NMOS as an input stage, and NMOS gate, we know the gate does not passes any current, so it has a very high impedance. So the good thing about it is like it will not drive any gain, and then it can also be easily used for amplifying stages. Like if you are getting a signal from behind, it can properly drive this common source amplifying stage and try to maximize the gain. So that is the advantage of having a high input impedance. And then frequency tuning, using the different elements in a single stage amplifier, like the dimensions of this amplifying transistor stage, or the resistance value, or the load capacitance, you can tune the frequency response of this amplifier. By tuning the frequency response, you can adjust its bandwidth, or you can vary its slope, like by how much the gain drops, like 20 dB, 40 dB. All those applications can be basically tuned with respect to a common source amplifying stage. And the good thing about it is like it is a very simple amplifying stage. It is one of the fundamental circuits for any student or any person who is entering to IC design or analog IC design domain. So since it involves very few elements, it is a good, basically a block to understand how basically analog circuit works. What are the different requirements or the criteria in order to understand and basically analyze any analog circuit or stage. So for that purpose also common source amplifier is a good starting point. So these are some of the basic points like why this circuit is used. So main out of like if I try to conclude this slide, so main agenda or requirement of a common source amplifier stage is to provide gain. So we obviously know like what is a circuit design. Like if you have a if you have a signal, you want to enhance its gain so that it can be provided to next cascading stage. So for that you need different kind of amplifier. So and common source amplifier is one of the fundamental circuits which is used for that purpose. Okay, so continuing with our overview. So here the schematic which is shown is this is an actual circuit. Like whatever symbols you are seeing or the nodes you are seeing, this is actual circuit which has been designed and fabricated on our test chip, which we will be testing in coming days. So this is how when you design a circuit inside any tool or EDA tool, like in our case, we are using an open source schematic editor tool called Xscheme. So this is how we represent it. So this is an amplifying stage, amplifying transistor, input transistor and MOS. This is a load transistor through which whenever you apply any input signal to the gate of this transistor, there will be some current flowing through this, and this current will produce an voltage drop across this. Based on the amount of current and the resistance value, there will be like appropriate voltage drop across this. But the issue is like this, the signal which is coming at output, it will be an inverting output. So but an amplified one, depending on the transconductance of this stage, this input transistor stage, and also the value of the load resistance. So all those basically criterias need to be taken care of whenever you're designing any circuit. So uh, as a designer, the requirement is like you want to design a 15 dB single stage amplifier. So you need to basically tune this, that's W by L of these transistors, and what will be the gate voltage and how much overdrive is required, how much will be the GM, and how much load resistance need to be used. Based on that, your gain properties will be decided. Here on the right side, you can see this is my input signal and this is the output signal. So there is some amplification which can be seen, and also the output is inverted, like the output is out of phase, like it is 180-degree out of phase of the input signal. So this is a common source amplifier is basically an inverting amplifier. Whatever signal you apply at input, the output will be 180-degree out of phase. And again, as I discussed in last slide, so it has a sufficient high voltage gain in the range of around 10 to 15 dB, or maybe you can enhance in some cases up to 20 dB, depending on the properties of your transistor device. And it has an high input impedance, and output impedance is also, it is not very low, but it is in moderate to high range. So basically, whenever you are designing some kind of a cascading stage, so all these criteria needs to be taken care of, so that neither the whatever output you are driving from this amplifier stage to another stage, so there should be proper loading so that the signal should not attenuate while going from one stage to another. So all those criteria needs to be taken, but it cannot be basically thought about independently. You have to take a complete chain, cascade chain, and basically analyze putting a common source amplifier in between and try to basically tune your signal chain, how much gain is required, what will be your frequency response. All those things are part of the design activity. So talking about this particular circuit chip which we will be testing, so there are two types of common source amplifiers in it. So this is a very basic and fundamental one with a resistor as a load. Like by resistor, I mean this is an actual resistor device which is fabricated on a silicon wafer. So we are using resistor as a load, actual resistor device to generate a gain, and another common source amplifier which uses transistor as a load. So how we can use transistor as a load if we are using it in a linear region. So we all know, or we can also use it in a saturation region. Basically, it's better to use it in a saturation region because there the resistance is very high. We want to basically use the resistive property of this load. And why that is, but why, what is the reason for that is because this the the area occupied by this transistor will be very much less as compared to the resistor. Although the resistance values attained from this PMOS load as a PMOS transistor as a load will be in similar range. For example, if we are trying to achieve 100 kilo ohm resistive load, so the area which will be occupied actually by on silicon by the resistor will be much more compared to the area occupied by this PMOS transistor. So basically, it gives us a good leverage. Like although we are getting a good resistive value from this PMOS transistor, but the area occupied is less. So that is one of our main requirement for any IC or VLSI circuit, that we want to basically optimize the area or minimize the area which is being occupied by that circuit. And what is the reason? Because the real estate on silicon is very costly. So basically, idea is to achieve your desired functionality, but using less silicon space on that wafer. So that is why sometimes not, but mostly we use only resistive or active transistor as a load. So that is what it is used. But in order to bias this load transistor, another current mirror configuration is required. And by applying a constant current or a bias voltage, we can bias this current mirror configuration and set up this load transistor in a certain configuration so that it provides a desired resistive value. And then we can achieve a desired gain from this complete transistor or amplifier configuration. So as can be seen in this configuration, load is replaced by a current source. There is transistor acting as a current source, and it generally provides a high voltage gain. And that is why, because we can generate very high resistance values from this PMOS transistor by keeping it in saturation region. And also the linearity is improved. So basically, in order to achieve a certain resistance value, it has to be in saturation region, and the voltage drop, that is VDS across this PMOS, can be very less. So what that means is like the output voltage swing which is achieved at the output node can be very high. And that means like if output swing is more, that your circuit is more into linear region. It will not be getting saturated with this PMOS transistor going into linear region. So that improves the linearity of your overall amplifying stage. So all these are benefits of this stage. But the inverting nature is maintained. So this is a common source amplifier. So that is a basic fundamental property of common source. Like it will always give you output as an inverting signal. It will be out of phase with respect to your input signal. And due to all these benefits like linearity and the low resistance, like have a high resistance value and using PMOS as a load, what are the fundamental benefits which you are getting is like we are getting high frequency performance and efficiency from this. Basically, PMOS transistor as load in common source amplifier. So all these are the benefits of using an active transistor as load. So in our test chip, the chip which we'll be testing, so both these configurations are available. If you want to test, whenever you decide to test it and book your slot, I will be there and helping you to make the measurement on these circuits, like how we apply the signals, where we apply the power supply, output, everything. We will do that setup and try to show you how this circuit is actually working and what happens when we change their biasing voltages. Like if DC voltages change, what impact will that have on the gate or the performance or the gain of the amplifier. So all these effects can be seen in actual testing whenever we do that. Okay, so these were the two schematics of those circuits, but obviously on silicon we have to realize it in a physical format using the fabrication layer. So these are the two layouts. This is the common source amplifier with a simple resistor load. This is your NMOS transistor, input transistor, equivalent to this amplifying transistor stage. And this is your resistor. This is how it looks like on silicon when you try to build your circuit. And this is input, this is output, this is VDD, VSS. So this is how a layout looks like. Similarly, for the another common source amplifier, we have all three transistors. You can see we are using 3 transistors here. So these are 3 transistors, and this is how they are connected: input, output, VDD, VSS, and this is the biasing state, biasing terminal. So this is how these amplifiers actually look like in a layout, and they are basically now integrated in a complete layout of a chip. This is a complete layout of a chip, which apart from these circuits consist of many other structures, and this is the location of these amplifiers in this complete chip. So now you can see, like, although individually they have a very big significance, but in scheme of things of a complete chip, they looks very minuscule or very small. So they do not even like properly visible. We have to zoom a lot in order to see them on the silicon. So this is like the scale at which we are trying to amplify the signal. And this is the benefit of VLSI and IC technologies, which we were discussing yesterday. If you would have to design a similar circuit on a PCB, you can think like how much things will be required. First, you have to take a discrete transistor in a package format. Then you have to take a resistor and put it on a PCB, solder it. Then PCB itself will have some size, but everything of that sort is basically accommodated in such a small area. It might be just 100 micrometer or even less than that. So these are the benefits of VLSI technology. Okay, this was all about the circuit, which is the first circuit in our training plan, that is common source amplifier. And but now how to test it? Obviously, we have a circuit, everything is available with us, but how do we test it? So in our case, we will be using this measurement device called DigiLent Analog Discovery 3. It is a very versatile and portable measurement device, and it can be easily powered using a USB. So, but generally, if most of you, I think might be from electrical or electronics background, you might have seen in your colleges or in your universities, if you have visited electronics lab, there are big bulky instruments kept in your labs. There are power supplies there are function generators, they are like sine wave signal generator, they are oscilloscope. So all those bulky devices are basically then connected to your PCB or your device and try to do the measurement. But now I think, okay, those things are still important and they are relevant and they are required when the performance is required or the accuracy is required or the like signal bandwidth, high signal bandwidth is required. But now in our case, we can use this like pocket size instrument. It consists of all the functionality which I just described. So let us go one by one to see what are its capabilities. So it can generate a signal up to 100 megahertz. Because anytime if you want to give some input to your any circuit, you need to generate different kind of signals, sinusoidal signals, and apart from its magnitude and its voltage ranges, you also need to decide like what is your frequency at what that circuit will be operating. So this device can generate signals up to 100 megahertz. And also it has 16 channel logic analyzer. So basically you can generate 16-bit, you can use it to analyze 16-bit digital signals also. So in our case right now, we won't be using that functionality because our circuits are mostly analog. So but if anybody wants to use, if some of you are working in digital domain, so for you also this could be a good alternative rather than buying very expensive and bulky equipment for your personal use. This can be a good alternative. It's also not very expensive. So okay, so this was an oscilloscope. It has an oscilloscope which can measure output signal up to 100 megahertz, but the input signal can be 50 megasamples per second. This kind of the analog and digital signals of different nature, like if you want to generate a sinusoidal signal or a square wave signal or a trapezoidal or whatever waveform you want to generate. So this kind of signals can be generated through it. Portability, it is very small. It is like as small as your mobile phone, and which also weighs that much only. So it can be easily carried anywhere. For power supply, it just needs to be powered through your laptop USB port. So you need not require a very sophisticated setup to power it up. And the good thing about it is like it comes up with a very strong and powerful software called Waveforms. That is a proprietary software from DigiLent to be used with this tool. So using that software, basically that software needs to be installed in your laptops, and whatever signals you need to see can be easily seen on this software using your laptop. So you need not require any separate display for purpose of seeing all the input and output signals. And that software also has several other benefits, so that we will be seeing in coming slides. So apart from this feature, what are the kind of analysis which can be done using this AD3 equipment? So we can do spectrum analyzer if you want to see like the how is the like signal magnitude or amplitude varies uh, in your waveforms with respect to frequency. So that can be seen. It can also do some kind of demodulation signal. It can see oscilloscope, all the transient waveforms like all the output and input that can be seen through oscilloscope. Waveform generator can be used to generate the input signals for your circuit. So, and power supply, obviously it has power supply, inbuilt power supply, which will be used to basically power your circuit on PCB. It can also be used for doing the impedance analyzing purpose, like if you want to measure the some kind of an S parameter signals or analyze convert them into S to Z kind of conversion, that can also, I think, is inbuilt in this. And then protocol analyzer, you can also analyze some kind of like USB or SPI kind of protocol, like digital signals, so that these signals can also be analyzed using this device. So basically, the point is like it is quite a good useful tool, especially for like academia or hobbyist kind of persons who want to have some setup at their end using which they can do some basic measurements on PCB. And good thing is it is quite affordable. So for our purpose, since most of you are from, I believe, from education background or research background, we will be using this equipment. And good thing is like it can be easily controlled using the remote setup, which we'll be discussing in coming days. How you can easily connect to this device on my machine using some remote software and try to do that as well. So if you are not actually at a place of your testing setup, and if you're traveling or you're away and some of your colleague is near to your testing measurement setup, then you can easily do some kind of remote setup to do those measurements. So all those are good features and capabilities which comes up along with this measurement device. Okay, so this is waveform software which I just discussed about. This is how it looks like. This is a screenshot from my laptop window. So this is how you will see it on your machine or laptop. Generally, whenever we are working in lab, so every equipment, if it is a waveform generator or oscilloscope, they have their own displays on which we see different kind of waveforms. So that is one reason why those equipment become bulky. But this equipment comes with a separate software which can be easily integrated on your Windows machine, and then it gives you an environment which is good enough to make all kind of analysis and measurements. And as I discussed, this waveform software is a pretty like useful and powerful software, and it provides various kind of analysis, all the things which I discussed in previous slide. And you can generate the waveforms from same software. There are menus and options here through which you can generate the waveforms and also control the parameters of that waveform, like whatever is the amplitude, phase, frequency, all that can be controlled here. And whatever waveforms you will generate and observe using this software, they will be real time. It's not like you are doing some kind of passive measurement, saving your data, and then viewing it on this waveform viewer. That is not the case. All these measurements which we will be doing and seeing, these are in real time. Like actually, the signals are transmitting from this equipment to PCB, and the PCB signals are measured on this waveform software, and they are real time. They are seen real time and visible on the display. Apart from that, I think I have not tried, but it also has some kind of post processing capabilities where you can capture the signal and try to measure its frequency, amplitude, rise time. All those features are also available here. And as I talked about, it is a very good tool, especially for like people who are in academia and who are learning, or if they are want to try some few things in electronics domain, or if they are building their own electronics project. So for that purpose, it can be a good tool to be used for debugging your circuits, or if you want to basically make some measurements and log that data. All those features are easily available and accessible using this device. Okay, so these are some of the like ports which are available with this device. This is how it looks like, and these are the different pins or channels available from this device, and these are the descriptions. I think uh, if you want to explore more, you can. I think there are a lot of material and videos available on this equipment on YouTube. You can explore there. But and I think it is very well described in detail there. But still, I will try to explain it briefly, like what is the purpose of all these signals here. So 1 plus 1 minus and 2 plus 2 minus, these are differential input signals. Like these are the ports from where the input differential input signal is generated. So if you want to generate a single-ended signal, you don't want to generate a differential signal, you can just connect your minus port to the ground of your measurement setup, so that you can just work with a single-ended signal. So these are the input signal channels, and then W1 and W2 are the output ports. If you apply the signal to this, it can measure like whatever signal is generated from your PCB or circuit. That signal can be measured through these channels W1 and W2, and their corresponding ground ports are represented using this down arrow. So these are the two channels which needs to be connected if you want to measure for example, in our case, output signal of a common source amplifier. So these ports will be used there. Then these are 1, 2, 3, 4, these are 15, these are the digital channels. If you are measuring some kind of a 16 channel digital signal, so these all can be applied here. So mind you, this is not a serial measurement, this is parallel measurement. So that can be measured through these channels. And so if you want to generate a power supply for your test circuit, like if you want to give a 1 volt, 2 volt, 3 volt, 4 volt or 5 volt. So these can be generated using these V plus and V minus port. And these are the reference. So it can generate both positive and negative supplies. So generally, for example, if you have some kind of a bipolar circuit, if you want to give a plus 5, minus 5, or plus 2.5 minus, for that V minus will be used. Otherwise, if it is not a bipolar circuit, it is like you just need a positive power supply. We will just use a V plus and this ground terminal to generate the DC supply voltage. And the maximum DC voltage which this device can generate is only 5 volt. So you cannot measure anything or any circuit which is more than 5 volt with this device. So that is one of the limitations of this equipment. Then these T1 and T2, these are basically terminals used for triggering a synchronization. If you want to do some kind of in-sync measurements or digital like signals or pulses. So for that purpose, these trigger signals are used. And wherever you see this down kind of arrow button on your device, this is all grounds. So these grounds need to be connected to your DUT grounds, like whatever PCB or setup you are using. To that ground of that setup will be connected to these grounds of this measurement device. So this is a brief description of this equipment. And next, this is our test board. This is how our test board looks like. And this is the chip which consists of all those circuits which we'll be measuring. And through this chip, through the pins of this chip, there are tracks coming to these pins, external pins, where we will be making the connections and try to do the measurement. But in order to make the measurements, we need to know like which pin is going to the input port or output port or VDD or ground of my required circuit. For example, in our case, let me go back. this is a circuit which we want to measure. So it has 4 ports: INP, PSS, out, and ground. So we need to apply signals to all these ports so that we can do the measurements: input, output, and power supply. So for that, we need to know which of the pins needs to is going to my required ports of my circuit. So that information is available in that table, and that is decided by how a designer, whenever he has integrated his design in a die area, in which pins or ports he has used to make those connections. So that is basically the responsibility of IC designer, that he should pass on this information to the test engineer. So I hope you remember yesterday I was discussing, like, IC designer and test engineer, they have to communicate with each other. They cannot basically do their work in isolation, because this kind of information has to be passed on in order to do any kind of testing or making a test plan. So for example, in our circuit, this test board for our common source amplifier, the VDD, that is power supply, is connected through this VCC D2 pin on this board. This is this pin. I have highlighted it using this red box. And so in order to provide a power supply to this pin here, it will be provided to V plus channel of AD3. So this is the V plus channel. I hope it is visible, this one. And okay, so to make the connection from AD3 to the test board, we will be using this fly wire assembly. So this comes with this equipment, and all the wires are pre-arranged as per the port channel functionality here. And a designer, or sorry, a test engineer, whoever is doing the testing, he will just connect this socket here, and use these wires to make the connections of AD3 to this test board. So here I have described, like, the V plus channel of AD3 will get connected to VCC-D2, and so similarly the ground, that down arrow, will get connected to the ground pin of the board. And so this will complete the VDD and VSS connection. Now for input, so input of the common source amplifier is going to the 24 pin, this slice here, and it will be connected to the W1 channel of AD3. So this will generate our input waveform, and then the corresponding ground of this channel will also short to the ground of this board. So wherever you see ground on this test board, these are all shorted. So this complete board has single ground. All the ground, it does not, even if you are seeing different pins here, but all these are shorted. So this becomes a reference ground plane for both your board and for your AD3 measurement, because for making the correct measurement, the ground should be same. Okay, so this completes input, and for seeing the out signal, the connection is made to IO23 pin. This is here, and this will get connected to the oscilloscope. That is it will get connected to the W1 to see the waveform. So this is how the IU input and output connections will be made. So whenever you will be doing testing, you give a request like, I want to do measurements on common source amplifier. So I will, at my end, keep make this setup ready at my end, make all the connections, and then I will guide you like how to do the setting, like what kind of signal needs to be applied, and what kind of waveforms, and how to vary the frequency, how to vary the basically the amplitude of your signal. All those parameters can be controlled, and you will directly try to control it using waveform software. So this one was for the common source amplifier with resistor load. I have mentioned it as CS1, and this is for the common source amplifier with active transistor as a load. So this setup has got an extra pin because it requires to measure, it requires to bias this transistor, current mirror transistor, so that proper like operating region of this load transistor gets defined. It works as a high resistance and gives you an appropriate gain as desired from this amplifying stage. And these are the respective connections made. So obviously it will have different connection. Okay, so VDD power supply and ground connection will remain same, but rest of the pins will differ because the placement of this circuit inside this chip is at different location, and all the ports are connected to different pins of a chip. So accordingly, so the port pins here are different compared to the previous circuit, and but the connection from 83 will be made similar like what we used earlier. Okay, so this picture shows you how a connections is made. So this is 83 device, this is the flywheel wires, and these are the connections made to the pins, respective pins here. So this is how a connections is made, and I think I have described these steps in previous slides, so no need to repeat it. When we actually do measurements, if you want, I can describe it further. Okay, so now comes the once let us say we have made all these connections as per this pin requirement, everything is made. Now we need to do the actual measurement, like how to give the all the required signals to our circuit. So this waveform software is installed in your laptop just like any other software you install on Windows. Whenever you open this software, so this kind of home screen appears, and on the left side there is a welcome button, and in this button there are all the tools and functionalities which are available in this software. It is available like if you want to generate power supply, DC power supply, you want to generate input signal, you want to see the scope, oscilloscope functionality or logic analyzer, all those functionalities are available and shown here on the left hand side. So whatever is your requirement, whatever kind of analysis or measurement you want to do on your circuit, you can select it and then make the setup accordingly. One by one, I will describe how in our this specific case for the common source amplifier, what kind of setup we have done. So that I will be covering. But this is what the software looks like when you open it for the first time. So the first thing for any circuit to be given is supply voltages. So without giving supply voltages, so there will be no proper DC biasing for that circuit. Okay, so you cannot make your circuit like if you just apply an input signal and there is no power supply, obviously that circuit will not work. The first signals which should be applied to the circuit is power supply. So in order to do that, there is a supplies menu in this waveforms home screen. I think this is that. You will click this, so this kind of window will open, which will open a tab called supplies. This tab will open on the top, and here you can make the setup. So this is as I told you, there are like there can be both the positive and negative power supply generated from this device, but in our case is not a it is not a polar kind of a circuit. We need not activate negative supply, we just need positive supply so that we can enable. So this green button will get activated, and then we can select whatever voltage or power supply voltage we need to give. So in our case, our circuit is working on 1.8 volt power supply. So that is what I have selected. And this is how you will basically set up the supply voltages of your circuit. So ground, it is automatically like connected. So you need not, you need to just simply connect the ground pin of 83 measurement device to the ground pin of your board. And then just give the uh, accordingly positive power supply voltage whichever needs to be given to your circuit for making it work. So this is how a setup for supply voltages are done. And then next is to give it the input signal to the our circuit. So in our case, since it is an amplifier, we would like to see it like by giving an input signal as a sinusoidal input signal to our circuit. So I want to generate a sinusoidal waveform. For that, I need to select this option WaveGen 1 from this again from home screen like here. If you Once the supply is set up, you just go back and press this wave. So this kind of tab will open on the top, and then you can do the setting of your input signal. For example, if I want to give it, I want to give a sinusoidal signal with some offset DC voltage, so that I can give it here with at offset. I can give it an 800 millivolt kind of an offset, and if I want to give it an amplitude of 1 millivolt, 5 millivolt, so that can be given. So all these setups, like which are normal signal generator functionalities, are can be done using this menu. So this will basically enable the input signal to your circuit. So first we did a power supply setup, then we did an input signal, like input signal. So in this case, we just have one input signal, but if somebody has some design has two input signals, so you need to accordingly make a setup for WaveGen 2 also. And then comes to once you have given the power supply and you have given the input signal, then what is required is to see the output signal, and that can be seen in this scope 1 option. So for that, again, you need to go here and select the scope option here, and this scope 1 window will open, and here you can see the here this is the scope 1, and here you can see the output. So this orange color waveform is the output signal, and this red one is the input signal. So all those whatever signals you want to see in this window on scope 1, you can select or deselect from here, and also you can adjust the basically scale of these signals, like how in which scale they are visible on this window. So all those setups can be done here once it is visible. And one of the last feature and important feature of waveforms is like this auto set. Whenever you do a setup, give power supply input, it is good to do enable this auto set feature. It is seen on the right side of your or right top side. It is kind of hidden in this waveform software window. But what it does, it automatically adjusts the settings of your oscilloscope on the input waveform generator, so that they are appropriately visible on an equivalent scale for the designer to make out a difference between them. So it basically does kind of a reset of your waveforms which are visible from the input and output side on the scope window. And it is required because for that, if a test engineer doesn't know like what are the voltage levels of my input and output signal, DC voltage levels, so he might struggle with making a setup of his waveforms and try to make them visible on his screen display. But if you do an auto set, so what it will do, like this software will automatically make those setups and try to show you the best visible view of your waveforms. So that is one important feature. Once those waveforms are visible, then you can go again back to a manual setup and try to adjust the scales and do and make the setups of scales on x-axis and y-axis, so that however you want to compare or see your input and output waveforms. So that setup can be done once the auto set feature has been run once. So okay, I think this was all about how is a common source amplifier looks like, and we also see like how we will be doing the measurements, what tool we will be using, what software we will be using, and how to apply the input and output signal. So the purpose of this lecture was just to give you a theoretical background, like how these activities are done. But I think theory is one thing, but doing it practically really matters. So I will strongly suggest you, like once the lectures are complete, you try to benefit take advantage of this opportunity, where we will be making this setup at remotely at my end, and you will be given a control to play with this software, like how to do the measurements, etc. Just go through these slides. I think you will get some idea of how it works, or there are several resources available online also, where you will get an idea, so that whenever your turn for measurement comes, you are a bit ready, like some background is available. And rest of the things, if you're facing any issues and trouble, I will obviously be there to help you and guide you like how these things works. So, and also one more important thing is like just read a little bit about common source amplifier, what exactly it is, how it works, what are its like input bias voltages, how to adjust its DC voltage, what kind of input signal needs to be given, how to change the frequency of the signal, and what will be the effect of increasing the signal frequency on the output signal. So all those, if you have some background ready with you, it will be more beneficial for you when you try to do the actual testing on this circuit. Okay, I think that's all from my side for today. If anybody has any query, yeah, you can please uh, share it on Q&A box. And also, I think, as I mentioned, please fill that online form. I received a lot of requests to join the Slack channel, and I have also sent the invitation to most of you. So please, whoever wants to join that Slack channel, I think it is important because all the resources, slides, and if lecture videos are available, we will be putting it on that Slack channel. So please try to join it. Fill that online form, which I had shared the link with you yesterday. I will, for the benefit of some of you who are new, I will again share the link here in the chat box. Yeah, I've shared the link. Please try to fill this form and try to join the Slack channel so that these slides which will be put there, you can get access to it and take a full benefit of it. So there are some queries. Is this measurement instrument applicable on other devices? So yes, it can be used, but it has some limitations. As I mentioned, it can only generate power supply up to 5 volt. And there is also some limitation on frequency range. So if your circuit is not very resource intensive or demanding, like it does not require very high power supplies or very high frequency ranges, then definitely it can be used. It's not like it will be used only for this kind of circuit which I'm trying to do it in this training. But first you have to map your requirements from your test circuit and then map the requirement of this equipment and then try to find like whether it will be good for your use. So any other queries if you want to discuss, please you can share your queries on Q&A box. Okay, if no more queries, we can conclude for today. And we will meet tomorrow again with another circuit which is part of our chip. And I will describe some basics about that circuit and also the methodology or steps which needs to be required to measure that. Okay, thank you everyone, and have a good day. We will meet tomorrow at same time. Bye. Good afternoon, everyone, and welcome to this third lecture in our ongoing lecture series on testing of VLSI circuits. So in first two lectures, we saw like what are basic the concept of VLSI circuits, semiconductors, and in our case, the circuits which we have designed, what is the approach we have used to design them and to integrate them, which foundry we have used, and all those basic concepts related to any VLSI circuits is design and realization were discussed in first lecture. And yesterday we saw like there are total four circuits in our chip. And we saw the first circuit yesterday. That was a basic common source amplifier. It is a very fundamental stage for any VLSI circuit, analog circuits. And also we saw like what kind of equipment we will be using for doing those measurements. So since we are working in a little bit constrained domain, like we do not have access to big measurement lab or testing lab, so we have a portable and compact equipment called Digiland Analog Discovery 3, and it's the third version of that. So we are using that circuit that it is well enough capable to do basic measurements, which I discussed yesterday, and some of the things I will repeat today also for the benefit of the participants. But the main focus of today's training is to do the testing, how to basically do the testing of operational amplifier using this equipment, analog discovery. So this is the main agenda for today's lecture. So let's delve into that. But before that, obviously, in order to do the testing of operational amplifier, we should have some concepts about what is operational amplifier. So let us first try to understand about it. So operational amplifier is one of the basic IPs or fundamental blocks which is used in IC design, especially for analog design. It has multiple uses, and its name, that is the word operational, its name came from the early days of analog computers when everything was analog. There was no digital electronics. So the engineers and scientists who used to build those computers used to, like, they needed to perform various mathematical operations like addition, subtraction, integration, differentiation. So all those were basically realized using the operational amplifier. So different operational amplifier can be used in various configuration to realize these kind of applications, but my mathematical application. So that's where its name operational amplifier comes from. And it is one of the most widely used basic circuit. It is also available in discrete form, like in an IC package form, but nowadays any complex ASIC or SoC, it consists multiple op-amps. It might have several op-amps as an IP used in that. So I don't think there could be any major analog or mixed signal or RF IC which does not have op-amp in it. So you can say it is one of the basic fundamental blocks of VLSI circuits. Okay, so before that, we need to understand what are the pins of this op-amp, like what kind of input signals, what are the output signals, and what kind of configuration is attached to the op-amp. So as can be seen in the this symbol, so any basic op-amp has at least 5 pins in it. So 2 are obviously power supplies, that is VDD and VSS, that is power to give the positive power supply or ground signal. Or if it is a bipolar op-amp, it will have a positive power supply or a negative supply attached to it. And then there are 2 input signals. One is the positive input and negative input. And so the relation of this is like whatever signal is applied to the positive input, it will cause a change which is in phase with the positive input signal, and signal applied to negative terminal will cause the change in the output signal, which is reverse to the phase of the input signal applied to the negative terminal of. So these are the significant, and obviously we have an output terminal. So these are at least 5 basic terminals which are available in any op-amp. But then if there are some other kind of requirements, for example, if you want to control the biasing of an op-amp, or you want to put some kind of a special switching circuit in it to change the gain or switch the gain of an op-amp from one configuration to another, or to change the compensation of an op-amp. So some kind of extra pins might be available in it. But generally, these are the 5 basic fundamental pins which are available in any op-amp circuit. And this is how a op-amp looks inside, like from inside. From the top, if you see a block diagram for an op-amp, it will look like this. These are the 5 terminals, but inside it has some specific architecture attached to it. So there are different configuration of like the transistors attached. There are some passive elements also used in it in form of a resistor and capacitor. So this is how an op-amp looks like. So now let us first see like what are these stages. So this is a basic op-amp, 2-stage op-amp. I think anybody who starts delving into analog design or IC design, analog IC design, they start with this fundamental block. So this is one of the basic op-amps. It has got 2 stages. So this stage, first stage is called a first stage differential stage. It has 2 inputs, positive and negative, and then this is the second stage. And this second stage is formed of a common source amplifier. This is the same amplifier which we discussed about yesterday, and which is also available for testing in this chip. So this is how I think I mentioned to you yesterday also, like how a common source amplifier, single stage common source amplifier is also one of the fundamental like blocks of analog design. So this is how it has find its use in op-amp circuit. And overall, this forms these 2 stages combine together to form an op-amp circuit. In between, we need to attach this RC combination, which is called a Miller compensation, which is used to basically adjust the phase performance of an open loop op amp, so that when it is used in feedback, so there is no stability issues in it. So this configuration of compensation is called a Miller compensation, and it plays a role in basically splitting the poles. There are two poles in this op amp. One is at the output stage of a differential amplifier, and the second pole is at the output stage of a common source amplifier. So these two op amps together uh, basically plays role in degrading the phase performance of an op amp. And by the use of this Miller capacitor, there can be basically pole splitting encouraged in this configuration, so that these poles move further from each other and a kind of a stability balance is realized. So this is just a basic understanding of an op amp. I think if you want to understand deeper into the configuration, I think you need to go through the theory of this op amp. But this is how a fundamental architecture looks like, and this is a biasing stage. Obviously, for any analog circuit, we need to provide some kind of a biasing. There are some DC voltages need to be applied, and how to basically generate the biasing current in this circuit. So this is a mirror configuration through which biasing current is provided to this mirror configuration transistor, and then this current is copied to this tail current source of differential stage, and also this current source in of a common source amplifier, and that's how a biasing is provided to this op amp. So this all together forms a two-stage op amp, and this is the same architecture which is used in our design also. So what are some of the basic features of this op amp? Is like it gives a good enough gain, sufficient gain, which is okay for most of the performances in analog design. It gives a gain of around 60 to 70 dB. But generally, if you have a very high gain requirement, so this configuration might not be suitable for that. For that, we need to move to some other architectures. Like we can attach another cascading stage, like a third stage, which can enhance the gain of this operational amplifier, or a cascade stage amplifier can be used. Op amp can be used. So this op amp is good enough if you want. Their requirement is of 60 to 70 dB gain. Another feature is that it is quite stable op amp. So its stability dynamics are well defined, like what is the dominant pole, what is the non-dominant pole, and how a pole splitting can be introduced in between them using the R and C values. So all that is well defined. So I think stability wise, it is very good. Because issue is like if you start increasing the stages in op amp, the more number of poles starts getting introduced, and then the stability performance get degrades, and maintaining that stability becomes in itself a challenge. So if a requirement is like you want a phase margin of 45 to 60 degrees, sorry, and open loop gain of 60 dB, so that in that kind of an requirement, this kind of op amp is good enough. So that's why I mentioned like it has wide applications. Like if you want to build some active filters or some kind of amplifiers, buffers, so most of those requirements can be sufficiently fulfilled by this architecture, two-stage Miller architecture. And below I have shown some simulation curves. Like this is the this op amp was I think connected in non-inverting configuration. So that's why this shows the gain. Like this is the input signal, and this is how the amplified signal looks at the output. Okay, so one thing about op amp is like although op amp in itself is a standalone circuit with all the pins, but it's all the benefits associated with op amp cannot be used in open loop configuration. By open loop configuration, I mean like you cannot use op amp like this. Like it is always all the benefits associated with op amp are always realized when it is used in a feedback configuration, because feedback provides a lot of other benefits with it. And moreover, there is some kind of offset voltage between these two terminals on an op amp. And if you try to use it in open loop configuration, then output will always saturate because it has a very high gain of around 60 dB or 1000 absolute number. So whatever, even if you apply a 1 millivolt differential signal in open loop configuration, you simply multiply it with 1000. So you can see there can be like a 1 volt peak to peak signal output just for a small 1 millivolt signal. If your signal is 10 millivolt, then obviously it will become something like 10 volt peak to peak. And then accordingly, the power supplies are not so high. If you sincerely use such a high power supplies with the op-amp to be used in open loop configuration, then the power dissipation through op-amp in open loop configuration will be very high. So basically, practically, whatever benefits you want to achieve, like you want to use it for these operations, or you want to use it as an amplifier buffer, most of these are beneficial if used in feedback configuration. And with feedback, there are other practical gains which are achieved with this op-amp. That is, yeah, the bandwidth of this configuration increases with the feedback. And then there are several other benefits also. So when you put this op-amp in feedback, this is how it looks like. These are some basic configuration. These are, I have included here just to show you an example. Like if you want some kind of a non-inverting gain, like your input signal is amplified by a, like, let us say, a gain of 3 dB, 6 dB, 9 dB, or maybe 20 dB. So you can use it in this configuration, and you can change the gain by switching the values of these feedback resistor. Similarly, for inverting configuration, the input signal need to be applied to the input terminal through this R1 resistor, and again the gain can be changed by changing the ratio of these values, that is minus R2 by R1. And if you want to use a buffer, it has a buffer. By buffer, I mean, like, if you want to drive a very high drive load kind of an element in your design, and it can basically introduce a loading on your following circuit which is driving that load. So in between you can introduce a op-amp. So op-amp will have a gain of only 1, but it will have a sufficient drive current through its second stage, that is at common source amplifier, and there will be no loading effect basically on this op-amp or the signal which is being driven through this op-amp while driving a further high drive load, which is followed by this source follower circuit or buffer circuit. So all these are basic applications. These are some of the few. There are several other applications like this. But this is the purpose is just to give you an idea. Like, this is how our op-amp looks like, and these are the basic configuration in which it is used. So I think, as I will repeat it again, like, op-amp is one of the most designed circuits in analog IC design, and it has several applications which I mentioned some here. And if you want to explore it further, I suggest you strongly to go through some good decent textbook and try to further read more about its theory. Okay, so in our case, the op-amp which we have used, the schematic of that op-amp is this. Like, this is how it looks like in schematic architecture wise. But obviously, when we have to put it on a silicon, we have to get it fabricated. We have to convert it into equivalent layer. So this is how this op-amp looks like. This is designed in Skywater 130 nanometer using open source tool chain, and this is how a layout of op-amp looks like. And when integrated this op-amp in our complete chip, this is the location where this op-amp lies in our chip area. And this die, the die of this design, which includes, apart from op-amp, several other circuits and some test structure, all that has been packaged in a QFN package and then mounted or on a PCB or test board, which we will be eventually testing. Okay, so this is just, I think, some of the stuff which I discussed yesterday also. So I will just quickly go through it just to repeat myself. This is a device which we will be using for doing the measurements. This is a Digilent analog discovery. This is a portable and a very lightweight measurement equipment. It is powered using a USB of your laptop. It can be powered using that. And it has the properties like it has an oscilloscope which can measure signals up to 100 megahertz, and it can generate the analog and digital signals waveforms using 50 megasamples per second waveform generator, which is inbuilt in it. And there's a very good support provided with this equipment in form of a software called Waveforms. I think that is the soul of this complete package. This software can be installed in your laptop, and that acts as a display for your measurement. And this is a cable assembly which gets attached to this device, and from there you can provide both the input signals and also measure the output signals. And this is how a waveform software looks like. So today I have brought actual device with me and also the test board which we'll be using for measurement. So at the end of lecture, once I finish my slide, I will just give you a small demo of how this whole setup looks like. So I think I can skip this slide for now. We discussed it yesterday also. And these are the basically symbols on this device, which gives you a reference of like what all signals need to be used for which purpose. Like these 1 plus 1 minus are differential channels which provide the input signals to your circuit, and W1 and W2 are the waveforms which you need to measure on the sinusoidal, that is for that purpose. Then it can provide 16 channel digital signals also, then power supply respective grounds. And trigger inputs, these are not required in our case. This is if you want to do some kind of a digital measurements. Okay, so this is our circuit. This is the schematic of our circuit. It has 5 pins. Okay, it has 6 pins. So there are two supplies, VDD, VSS. There are two inputs in positive, negative input, output. And then there is one bias node also. So the purpose of this bias node is like by changing the voltage and this bias node, you can change the bias current through this current mirror transistor, and also control the bias current to the tail current source of this differential stage and the output stage. And accordingly, you can control the performance. Like you can see like what kind of offset values are coming or how much the properties of your op amp is changing. So this is just a kind of a tunability. For purpose of tunability, this pin has been allocated here. And these are the respective signals of these pins of this op amp. So this is the VDDA. This is connected to V plus of AD3, and respectively, I think all these pins are mentioned here, like which pin of my AD3 goes to the connector pins of VDCO goes to the pins on the test board. And these pins are also highlighted on the test board, like which all pins are being used for the measurement of this op amp circuit. So I think this is self-explanatory. So you can just try to go here and try to read these pins and what all connections are made from AD3 to these pins, and also correlate it with this pins which are highlighted on this test board. And this is how configuration for op amp looks like. So this particular configuration, I have used put this op amp in a source follower configuration. That is okay, let me just go back to this schematic. For testing purpose, I have put this op amp in this configuration, source follower, that is output is shorted with the input so that the gain of this op amp is 1. So this is what I have done here. So the output pin of an op amp is shorted to the input pin through this blue wire, and rest of the connections which are mentioned here, like VDD and all the input and output pins and bias pins, all those connections are made according to the configuration explained in this table. So this is how the connections are made through my device to this test board here. Okay, so let me now go to, I will try to show you my now the board. And I think these steps which I have covered in remaining slides, this one, it's the same, similar to what I described yesterday for the common source amplifier. And I will try to show you them on live by sharing my screen and also showing you test board. So I will just disconnect my slides for now. Before going to the waveform software, I would just like to show you how the setup looks like. So this is the test board. I think I'm not sure how well I would be able to show you. So this is the test board which we are trying to measure, and all the circuits which I am covering in this training lies on this test board. And this is the analog discovery equipment. And this is the connection which I have made to this test board. So today, the configuration which I have used is for a op amp. and I have put it in a source follower configuration. And now I will try to show you how I will make the settings or setup on the waveform software, and also try to describe all the steps, how basically this software has to be used. And whenever you want to do this testing on your own, like later on, whenever you book the slots for this testing, so the steps which I am performing today, so these similar kind of steps you will also be performing later on. Okay, so let me share my screen now. Okay, I hope you are able to see the my screen, that's the waveform screen. Can just somebody just confirm whether you are able to see my screen through chat box? Are you able to see my screen? Okay, thank you. So this is how our waveform software looks like. If you okay, so before that we need to make these setup, like need to connect the board with the measurement device and all the connections, cable connection, which I have shown in the previous tables covered in my presentation. And after that, need to open our waveforms. You first of all need to install it on my laptop, and then need to open it. And once I open the software, this kind of a home screen appears. So as I mentioned, first thing to be done is to give the power supply to your circuit. So this is a supplies menu, and this is my positive supply. For example, I am for this op amp works on 5 volt. So from here I can set up 5 volt. So there is no negative supply used. So this has to be disabled. Okay. This is disabled. So now 5 volt means, so whatever the appropriate pin is on the analog discovery, it will generate a 5 volt DC voltage, and it will pass on the equivalent pin on the test port. And then from there, it will go to the pin of my chip, and which is connected to finally to the op amp power supply. So this is how a power supply connection is done. After that, once a power supply is given, the voltage is given, we need to set the input signals. So these are the input signal. Need to open a wavegen menu using this option. So this kind of a tab will open, and then there are multiple channels here. So since I need two kind of input signal, one is the input signal to the op amp, sinusoidal input signal, and another is a DC signal which I need to give to the bias pin. Okay, so let me just open my slide and show you from here also. Okay, so these are the input signal I need to give. So this is what I am setting using this channel 1, and then another signal to be given is this bias DC voltage. So this I will provide using channel 2. So for giving an input signal, first I need to define a DC level at which that input signal will lie. That input signal will lie. So that DC voltage is defined using this. That is 2.5 volt I have used DC voltage. You can select any other voltage if you want. So this, since this is a 0 to 5 volt op amp, I have used a center middle DC voltage as an offset here. And then this is a 100 millivolt peak to peak signal I'm applying. Not peak to peak, this is just a peak signal. So basically it means it is 200 millivolt peak to peak. So if you want 100 millivolt peak to peak, just put 50 milli here. So now the signal will be 100 millivolt peak to peak. So it means like the sinusoidal signal will go, positive peak will go to 2.55, and the negative will go to 2.45, and then there will be 100 millivolt sinusoidal signal. And the frequency of that signal can be changed using this, like 1 kilohertz I am using. So this is how you generate a input signal, sinusoidal input signal to your op amp, and this is connected to the positive terminal of op amp. And now in order to give a DC of voltage, I will just use a DC from here, this menu, and give an offset of 800 millivolt. So this just generates a 0.8 volt DC signal. So after that, once I made all the connections, I need to see the oscilloscope functionality in this software. For that, I will and open scope. So this kind of menu will open. So this is where I will see all my signals. Like if I want to see what is my input signal, I will enable this WaveGen one. If I want to also, for example, let me show you. Before that, I need to enable this run all. So right now, this is not, I have just made the setting, but this is not active. So to make it active, I have to run all. So now both these signals become active. And you can see this is how my input signal waveform looks like. So this is my WaveGen 1. Like this is my channel 1 sinusoidal, and my channel 2 was a DC signal. $800 millivolt signal. Let me just set. Okay, so this is my DC signal, 800 millivolt, the bias signal. So both these signal can be seen. So now the scale or the basically y-axis scale of this is disturbed. So that's why you are not able to see the signal like I was seeing earlier. But let us for this move to enabling these signals on this device. So right now, whatever signals I have set, they were disabled. So before doing the actual measurements, I need to enable this. This is off. So now this is enabled. And now this is also on. And now I will go to my scope and try to do the auto set. Okay, so basically by default, whenever you switch on your power supply and switch on your input signal, the scope will capture the signal as per its default settings, whatever the settings are in this display. But if you want to see all these signals basically accommodated in a same display, it has to adjust these scales on the y-axis and also time axis. So for that's why we need to for the first time whenever we have changed our signal or anything, we need to do auto set so that this software itself will adjust the scales of all your signals and output input whatever channels you are using, and accordingly make them visible accordingly, like with respect to each other. You want to measure input and output signals, so this scale should also be visible proportionately. So that's what this auto set feature does. But now this x-axis scale is in nanoseconds. So I do not do, but my input signal was in kilohertz range. So I need to change the x-axis scale also, so that I can do it from here. Like if I want to do it in milliseconds per division. So that's how it looks like. Okay, so now I can try to check what are these waveforms. So WaveGen is my input signal. So WaveGen is this red one, this one. And channel 1 is my output signal. But now you see the scale of these two are different. Like this is 50 millivolt per division and it is 20 millivolt per division. This is not one-to-one comparison. So I need to make the scale of them both same. So I just make it 20 millivolt per division, and this is how like the signal looks like. So since this op-amp was connected in like source follower configuration, this is one of the simplest one to do like practically. So that's why I have used this, because if you have to do an inverting or non-inverting configuration, then you have to use some extra elements. You need to take the resistor, etc., and make the connection and check their ground and short the ground of your resistors with the ground of your measurement device. So all those complexities are there. So that's why I took this simple example. And so source, what is the basically functionality of source follower? It just replicates input signal to the output with the gain of 1. So that's what we are seeing here. And these whatever perturbation you are seeing on this output are most probably noise. So there is some limitation, like you cannot do a very high fidelity measurement with this setup. But this is the basic purpose, like which you want to see, like how my op-amp is working in which configuration, that can be easily relied. But if you want to do a very low noise measurements, obviously you need to move to a proper measurement setup, which requires sophisticated equipment and other setup requirements. So this is how measurements are done. So now if you want to play with it, like you want to see what is the effect of like DC voltage, bias voltage applied to, I can just try to change the bias voltage and see is there anything happening. Okay, so I think there is some offset getting introduced now due to change in this bias voltage. So this is a positive offset voltage getting introduced. So let me now try to decrease this offset voltage. Let us make it 700 millivolt. Now you see the output signal goes below the input signal DC voltage. So now the negative offset is getting introduced. So all these things, experimentation based on the theory of the circuit can be performed using this kind of a setup. Okay, so I think that's what I was trying to cover in these slides. Let me just quickly go through this. Whatever we have seen in the practical measurement setup I have covered here. So this is the menu which is used to enable different options in waveform software like power supply and waveform generator and oscilloscope. So this is where you enable those. And then to set up the supply voltage values, this is how it can be done. And this is the menu in which the supply voltage options are available. And then if you want to set some kind of like a varying time variant signal like a sinusoidal or pulse or anything, this can be set up using the wave chain option, and just use the first channel of this, and there you can set the DC voltage, offset voltage of a signal, and or the peak amplitude frequency, whatever the parameters you want to play with, all this can be done here. And next, if you want to add another channel, like there are, let us say, two kind of signals, two input to be applied to a circuit. Like in our case, apart from the sinusoidal signal, we also need to give a DC voltage. So that's can be provided using this, like channel 2 can be enabled, and then this format can be changed to DC, and accordingly our DC voltage can be changed. So mind you, so I think there is a limitation with this setup, like you can only provide two input signals. If you need more signals to be applied, like there are three or four signals to your any circuit other than op-amp or whatever circuit you are using, then obviously you need to use an external signal generator. So this is what some limitations are. But if you have a small circuit, like generally we have, analog circuits which have more less than one or two signals to be applied, so for that it is good enough. And once the signals are applied and supplies are generated, in order to see the output signal, you need to enable the scope menu. And in scope, I showed you, like you need to, once the scope is open and all the other uh, options are enabled, you need to do the auto set feature for the first time so that all the waveforms are appropriately basically synchronized with their scale and are visible on your display. Once it is done, then you can check like whether their offsets and everything ranges are same or not. If you want to do one-to-one comparison, try to make their range same. So all this can be done in this scope option. So it's basically a oscilloscope kind of a functionality in this software. Okay, so this is what auto set is. I think I have explained it, and we have also seen it actually how it works in today's demo. Okay, so I think that's pretty much all from my side for today. And I think I have already shared the link. If you anybody, I think a lot of you have joined the Slack channel through the online form shared with you. But if anybody is still missing, so they can please join this form. Link has already been shared in chat. So that because I'm sharing these slides on this Slack channel, and if you want to access this slide, please join this Slack. So I think that's all from my side for today. If any queries are there, we can quickly discuss it. So there is a query by Afsar, like, is this measurement instrument applicable on other devices also? So yes, Afsar, you need to like see like what kind of device is that, like how many input signals or power supplies it required. If it requires like one or two input signals or only one power supply and it has only one or two output, then this device can be used for those kind of measurement. Obviously, the connectors which you need to use has to be basically in sync with the connectors available on your test board. So right now, the connectors which are available with this test board, like whatever equipment are these are called Birch connectors. So if your test board already has Birch connectors in it, so you can directly try to use this measurement equipment. If you do not have Birch connector on your board or on your setup, then obviously some kind of a connect adapter or connectors need to be added in between. So that is a kind of a compatibility issue that needs to be resolved. So first you need to check like what are your requirements, what are input, output, power supplies required for your circuit, and what are the options available in this equipment. So you can just try to go to its website and all the technical information is available there, and then see whether actually you can do the measurements or not. Okay, so there's also one more option. If for example you need four input signal, but you only have two inputs in this equipment, so you can use two other input from external signal generators. You can use the oscilloscope and all the other measurement capability of this equipment. So that kind of compatibility options can also be explored. Okay, so I'm again sending the link. Please see the link on chat. I have shared it again. Are there any other queries? So I think somebody is asking query about the video. So let me check uh, I need to check with Academy 32 like how the recording of these videos can be made available to you. So if there is any update on that, I will put it on Slack. So please remain tuned to the Slack. So all the communication or updates will be shared on Slack whenever recording or slides are available to be uploaded there. So any other queries, please, if you have any other queries related to design or general semiconductors or any other topics you want to discuss related to this field, you are most welcome to ask. So if I have the capability to answer, I will definitely try to resolve your doubts. You can put it on Slack also if you're comfortable that way. Okay, so Abdul is asking how can we measure the open loop gain? So Abdul, so for actually measuring the open loop gain, first we need to compensate the offset voltage of this op amp. So first, offset voltage of op amp needs to be measured by putting it in a closed loop configuration. So whatever is the offset voltage between the input and output, that needs to be calculated or measured by checking the measurement waveforms. And then that offset voltage needs to be compensated on either the positive or input terminal by applying using it in open loop configuration. And after doing the compensation of offset voltage, you need to add a very small signal. For example, if your op amp is a 60 dB gain, it means it has a absolute gain of 1000. So, for example, if 1 millivolt differential signal is applied after offset composition, so you expect to see a 1 volt peak to peak at the output. So all that setup needs to be done before you can do an actual open loop gain measurement. And so it's not so easy or simple. So there is kind of a background setup needs to be done using all the setups like on a breadboard or PCB. You have to make a test circuit for that, and then only you can do that measurement. So that's why I think this also emphasizes my point, like why the test engineers have a critical role, because all this kind of analysis of visibility for measuring a particular spec of a circuit needs to be analyzed by a test engineer, and he only takes care of like what kind of compensation or configuration and what kind of components need to be used to do a particular specs measurement, and also then to ensure like whatever measurement he or she is doing, they are accurate. So ultimately a measurement only makes sense as long as it is accurate. You have to take care of all the noise and other like interference uh, issues during the measurement. So yeah, Abdul, most of the specs of op amps need to be measured in closed loop. But since you specifically talked about open loop gain, for open loop gain also, first you have to do a closed loop measurement, take a offset voltage value from there, and then try to use that number while doing an open loop measurement of an op amp. So can the AD3 measure the frequency response? So it cannot do a direct measurement of frequency response like we do in simulation, like you see a dB plot, gain plot in dB with respect to frequency. That type of measurement cannot be done. But what you can do is you can change the frequency of your input signal and keep on changing it and try to measure the corresponding output amplitude. And then once all the measurements are done, you take that data, put it in Excel sheet, and then try to do a gain versus or output magnitude versus frequency plot. So that way it can be done. It's not the way we do it, the simulation in schematic or in the circuit. So there are way to do it, but not it is not as simple as done in simulation. So you have to basically manipulate it and do those measurements. And then once the measurements are done, you have to do a post analysis of those measured data in some other software, maybe Python or Excel, whatever, for post processing purpose. Any other queries? Okay, thank you. Then I think we can conclude for today. And I will be putting the slide of today's lecture on the Slack. If anybody wants to access it, you can access it there. And we will meet tomorrow with our next circuit, that is bandgap reference. That is a very pretty simple measurement, I think. So, okay, so let us meet tomorrow to check on that. Thank you very much, and have a nice day. Bye. Good afternoon, everyone, and welcome to today's fourth lecture in our ongoing series for to learn how VLSI circuits are tested. And I also gave you some introduction. So, okay, so before we start, can you confirm everybody is able to hear me and also see the slides? Just would uh, confirm this in chat box so that nobody is having any issues. Can you confirm in the chat box? Are you able to see my slides? Okay, thank you. Okay, so till now we have seen the introduction to VLSI circuits, and also we saw about the process in brief about how to design these circuits and how our designs are integrated, which all circuits will be used for testing. And also we saw first two circuits in last two lectures, that is common source amplifier and operational amplifier. They are both basic fundamental circuits which are required for any analog circuit. They are fundamental blocks, or also called as an IP blocks. Now we move to our third circuit in the series, that is bandgap reference. So let us briefly see what is bandgap reference. So the okay, so in any IC or any analog circuits, what we want is like all the circuits which are designed, they should be consistent. By consistent, I mean they should not change with the change in their environment or in the conditions. By condition, I means like for example, a circuit can be used in very cold environment, cold places, or it can be used in very high heat temp kind of temperatures. Like there are ICs used inside uh, vehicles, inside the engines or in the assembly of engines of the vehicles. So there the heat temperature is very high. And if you want to use any electronic circuit or any product in very cold temperatures, so the temperatures will very also be very low there. So all these environmental conditions, they can affect the performance of your circuit, because as you can understand, whatever these things are, these are ultimately some materials which are used to fabricate or develop these ICs. And also the scale is very small. So obviously, based on the temperature, the properties of the materials which are used to build these ICs, those changes, their resistance and their properties changes, their mobility can change. So all these parameters basically affect the functionality. By functionality, I mean it might altogether stop the working of that device, but it can also change. For example, if you have designed an op amp or an amplifier for 60 dB gain, maybe if the temperature conditions change around it, if the gain might drop to 50 dB, or it can increase to 70 dB. So obviously the consideration which you have taken to design that op amp or use it in your application, that changes. So that will have a negative effect on the performance of your circuit. Similarly, supply voltages. So we know, like, although we design our circuits to be robust to the supply changes, or we want our supply voltages to the circuits to be same, but we can have some malfunctioning in supply voltages. So that can also affect the performance of your circuit. For example, if you designed your circuit for 5 volt, but the supply so DC voltage which is getting supplied externally to that circuit goes down to 4.5 volt, where it gets increased to 5.5 volt. Again, that can affect the uh, basically the specifications or performance of your circuit. And again, the next step is process. So by process, I mean during fabrication, all the procedures which are taking place inside fab, these are called process steps. So it's not, although the control of fabrication processes is very stringent. Like the foundries ensure like whatever processing is happening on different wafers and different lots, they are consistent. Like there is not much variation. But still, since we are talking about the dimensions in micrometers and nanometers, even a small change in process or the property of a chemical used or material used to manufacturing, they can have effect on the feature size of a layer which is getting developed on a wafer. And if a size of a layer changes, or the thickness changes, or the width is not properly as per the dimension, that again will change the properties of that material, and ultimately it will affect the performance of your cell. So all these variations are possible during the process of manufacturing. But the role where the band gap plays is that what that the okay. So one more thing is, for any analog circuit, for making it work, first thing which is required is to properly bias it. By biasing means you have to give a constant voltage to it, or a constant current, using which it will generate the proper biasing voltage inside that circuit, and then only you can try to derive the required application or performance from that circuit. If that bias voltage changes due to any of these factors like process or supply voltage or temperature, then obviously the circuit which that bias voltage is supplying to, it will also change its properties, and it will not work as per the simulations done. So purpose of band gap reference is to give generate that particular voltage which is constant. constant with respect to the process supply voltage and temperature variation. In IC design domain, we call these variations as PVT. So whenever you hear a term called PVT variations, you can understand like a person is talking about that whatever the performance of that circuit or chip is, it should be invariant to those PVT variation. So that is the purpose of bandgap reference. So as can be seen in this example, this is an LDO circuit, and at the input of LDO, we have one reference voltage which is required to generate a reference voltage and make this the operation of this LDO circuit. So it is very important like this reference voltage should be constant, because then only this output voltage generated from LDO out will remain true to its performance. So for that purpose, we need some kind of a circuit which can provide that constant voltage. So this is one example of a bandgap reference, that it is providing a constant voltage. So this voltage BGR out, it won't change. If even if your VDD, which is 5 volt, it may deviate to 4.5 volt, 5 volt or 4.2 volt or 5.5 volt, this voltage will always remain constant. And generally, the bandgap reference voltage in CMOS technology is around approximately 1.2 volt. That is because of the bandgap properties of the material. So this bandgap reference voltage is always 1.2 volt. So if you know like my LDO voltage input will always be constant 1.2 volts, accordingly you can design rest of the circuit. So that is what is the requirement of bandgap reference output voltage in this particular circuit. Similarly, if we are designing an op-amp or any filter where there is a requirement of constant current or constant voltage biasing, there again the bandgap reference plays a critical role. In fact, it can be said like just like an op-amp is such kind of a circuit which is used almost in all the applications which are analog in nature, or any IC will have some op-amps in it. Similarly, any IC will always have some kind of a bandgap reference in it, because that bandgap reference is a constant voltage based on which all the other biasings takes place in that circuit. So again, it becomes a very critical part of IC design. So I think these things we have discussed. Temperature stability. So So I talked about a voltage variation, but temperature also generally, whenever we are designing any integrated circuits, we take a range of -40 to 85. That is an ambient temperature. So these are the conditions of which exist in our day-to-day life or in different kind of environments. So this kind of a temperature variation can occur. So if you go to very cold places, like if you want to take your mobile phone to, let us say, Antarctica or some Alaska kind of places, so there you will see sub-minus kind of temperature. So you want your electronics or the circuits which are used inside your gadget to work properly there. Similarly, if you take it to very hot places, like in Middle East or some other places, or if you are using it in some kind of an environment which is very hot, like just I give you an example of a internal combustion engine in a car. So there are a lot of chips or ICs inside cars, nowadays. So there the temperatures are very high. So all those environmental conditions, the circuit should survive. And the good thing about VGR is like even with those temperature variation -40 to 85, this voltage generated out of it will always remain constant. So once you get this constant voltage, the remaining circuitry around it you can develop confidently. So you can be assured like even with little bit of the variations, the performance of your circuit won't degrade too much. So again, by robustness, I mean, I gave you an example, you want your circuit to be robust. It means it can work in any kind of harsh environment, by harsh, I mean like the temperature swing which it can see around it. So that gives you the robustness to your product or IC, which that product is based upon. Again, efficiency, by efficiency, I mean the BGR, there are okay, so before going to the efficiency part, so VGR is one way to provide a reference voltage to your integrated circuit. So there are several other ways through which you can provide a efficient kind of a reference voltage to your IC. Like you can use a simple resistor divider circuit, or you can use a Zener diode kind of, or you can use a kind of a PTET or CTET kind of circuits, so that there is some relation to the temperature to the voltage generated through them. But all those circuits are not very efficient, like they will consume significant amount of current. But the good thing about BGR circuits are they take very low amount of current, so the power dissipation through these are very less. So that's why they are very efficient in IC design, because ultimately we want like the circuit or chip should consume as little power as possible to make it more efficient. Okay, so by compact, I mean the number of elements used in BGR are also very less. There are few elements required in it, and the layout area, the real estate which that the layout of the BGR design occupies on a silicon is also not too much. Like as compared to the other circuits used in your IC, the real estate occupied by BGR is very less. So if so, by that comparison, it occupies a very less space. So that's why we can say it is a compact solution to generate bias voltages. Okay, so now let us just look briefly about what is the principle of BGR operation. So basically, we want like our circuit should be, the most important thing is to make it temperature independent, because that is a critical part. So once we make it a temperature independent, the other aspects can be taken care of. So for that purpose, there are uh, two properties which are taken care of. Using those, like the amalgamation of these properties, we can generate a constant bias voltage through bandgap reference circuit. So these are called PTAT and CTAT. So by PTAT, I mean it is mean like positive temperature coefficient. So in our bandgap reference design, we need to generate kind of a current which is proportional to absolute temperature of that circuit. So by, as you can see in this right curve, like PTAT is like the reference voltage of that part of the bandgap reference circuit is proportional to the temperature around that circuit. So that kind of a voltage needs to be generated in that design. Similarly, CTAS is complementary to absolute temperature. So as can be seen in orange line, so we want to generate a reference voltage which is complementary to the temperature of the circuit. So using these two inversely properties of voltage inside a bandgap reference circuit, we can try to cancel out the currents generated due to these voltages. And what we will get in end is kind of this constant line shown in black. So there will be no temperature independence. So how this is done is like won't go in detail of this circuit, but this is how a bandgap reference circuit looks like. So there are three diodes used in it. Using these two diodes on the left hand side, by choosing their dimensions and the amount of current passed through them, PTAT voltage is generated across this R1 resistor. And then the current which is generated through this R1 resistor is passed on to these through these current mirror transistors, and then passed through this Q3 diode, Q3 PNP transistors, which acts as a diode. And the voltage across this Q3 is kind of a CTAT. So basically, PTAT current generated through R1 is passed through Q3, and then their ratio is adjusted so that these two complementary current variation properties cancel out each other, and whatever voltage comes out in and at the VREF node is constant with temperature. So this is a basic. I think I'm trying to make it very brief just for your basic understanding. So this is how kind of a PTAT and CTAT properties of BJTs are used to cancel out their temperature variation and generate a constant voltage through this bandgap reference circuit. So this is a basic functioning of bandgap reference circuit. So as you can see, it uses not too many components, and also it doesn't have any kind of an input or input kind of a signal in it. It is just a DC circuit. It just has two power supplies, VDD and ground, and an output. So this is a very small circuit, and that's why, as I mentioned, one of its advantages, like it is very power efficient. It doesn't consume too much DC power, and also it is very compact in nature. Like it will occupy very small space in layout. Okay, so in our case, the in on this chip, the bandgap reference circuit which we'll be testing is this one. So this is how our circuit looks like. So it you also using an op amp. The purpose of op amp is to act as an error amplifier, so that the voltages around these two branches of PNP transistors, they remain like constant voltage needs to be generated, generate a kind of a level current around these two branches. So this is how this architecture looks like. And one important consideration about bandgap reference circuit is like it needs a startup circuit need to be added to here. So why startup is required is because sometimes when the voltage that is on the VDD node, the voltage is ramping on this circuit, like For example, when you first time switch on the power to this circuit, it won't immediately move from 0 to 5 volt. It will take some time to ramp up. And sometimes these kind of circuits which include too many loops in it, they can go into a zero current state or a meta state kind of a phase where they attain a state where no current or DC current is flowing through them. So we want to prevent that kind of a situation. So that's why a startup circuit as shown using these three transistor on left is used so that this circuit does not go into zero current state and starts functioning properly. So that's why startup circuit is should be used with any bandgap reference design. And this particular circuit is designed in Sky 130 CMOS technology, and obviously we have used 5 volt transistors, and also the PNP junction PJTs transistors are used with in design of this. So one thing about BJTs in CMOS technologies are like they are not kind of developed exclusively as for the purpose of a design of a BJT transistor in CMOS technology. So based on whatever processing steps are involved during the fabrication in CMOS, using those layers or those steps only, we try to implement a BJT in CMOS technology. So it is not a very high efficient BJT design, but the purpose of using a BJT is because it gives us access to PN junctions, and it is a temperature coefficient of PN junction which are required in order to generate PTET and CTET voltages for design of bandgap reference. So that is our main requirement of using vertical PNPs, and that these transistors serves that purpose. So that's why this is are mostly used these vertical PNPs in CMOS technology for design of bandgap reference circuits. Okay, so this is, I think, brief about bandgap reference. So I think I have tried to quickly tell you just about the significance of bandgap reference, like why it is required and what is the basic functionality of these circuits, how they work. So now let us look at, okay, so this is the bandgap reference circuit design or layout which is used in our chip. So this is what we will be measuring for the testing of this circuit. So ultimate aim is like we want to see the output voltage of this circuit, whether it remains constant or not. So I think the main requirement from this circuit is that. So that we will just see during course of this lecture. And this is where this bandgap reference circuit lies. Okay, so this is the place where in our chip this circuit lies, and so the connection to this circuit to this is VDD, this is VSS, and there is somewhere output of this chip there. So the connection to these ports of this layout are made through these pins available in this chip, and these pins are then connected to our final package pins, and then those pins are connected to the tracks on the PCB through which we will be giving the supplies and measuring the output signal of this circuit. Okay, so this is, I think I have discussed this in last two lectures for, okay, I will just repeat it for somebody who is new for today's lecture. So this is the device which we will be using for the measurement. This is the Analog Discovery 3 device from VLSIand. It is analog and digital measurement device. It can do both kind of measurements, and these are the features. Some feature of this device: it can measure. It has an oscilloscope functionality where it can measure signals up to 100 megahertz, and it can generate different kind of waveforms, analog, digital, using the 50 mega sample per second waveform generator. It is quite portable, as I mentioned. It is it is handheld kind of a device, very small. It can be carried in even in your pocket. So you need not have a sophisticated measurement setup to make a small measurement using this device. And it has got a software integrated with it called waveforms. So I think that is a very USP of this circuit, which gives it a lot of functionalities through which you can control all the features, what kind of waveforms you need to generate. I will just show you a demo of that. And these are the different functionalities which are available in this equipment. It can do spectrum analyzer, signal demodulation, oscilloscope, waveform generation, power supply, impedance analyzer, protocol analyzer. So all these functionalities, generally, if you go to any lab, so I think for each of these individual measurement, you need a separate equipment. But this equipment has all this functionality inbuilt in it, obviously. But if it is a very small equipment, so there are some limitations with it. So the major one is like it can only do measurements up to 5 volt. It has a power supply limitation of 5 volt, and there is a frequency limitation of 100 megahertz. So don't expect it to use for like a very extensive measurement or testing, but for small signals, analog digital measurement, I think this is a good enough solution. And it has it since it is very affordable, it's not a very costly equipment. It can be easily used for like for academia, or if you are an hobbyist, you want to do some kind of your own testing or measurement, so it is an ideal solution for that. Okay, so this is the waveform software. We will just see it, and this is where all the setups and measurements are done. This is installed on your laptop, and you can do all the control of signals, signal generation, and you can do the live visualization of both the input and output signals using oscilloscope function on this software. So all these are like quite a good features of this software. It gives a good package, basically advantage to this solution, the digital and analog discovery. So, okay, these are the channels and ports which are available. So these are the W1 and W2 are the analog signal generations of this device, W1 and W2. And these are the input channels of this device. So by input means these are input to this device. So basically this is the output of your DUT or circuit which you are measuring. So these are differential channels, two differential channels, one plus, one minus. If you are using measuring a single-ended signal, so the other one minus and two minus, you can just ground them so that your single-ended signal can be measured using these two channels. And these are the two analog signal generations. Then there are digital signals, 16 channels, digital signals you can generate from it, and then power supplies and other reference and ground. So trigger signals can also be generated from here if you want to generate kind of a clock signal, or if you want to interface this device with some other equipment for measurement or some other purpose. So these trigger signals are useful for that requirement. So, but for our case, the kind of measurements which we are making analog measurement. So these two are the major requirement. You want to generate an analog signal from this device and also measure an analog signal for this device. So these two features will be used for our requirements, and also generate power supplies. Okay, so this is the test port. This is our chip. Here inside it lies our design. And in order to measure that design, these are the signals which needs to be applied. So as I showed, a bandgap reference does not have any specific input signal to be applied to it. It is a kind of a DC circuit which just generates a constant DC voltage. So it just reads a VDD and ground signals power supply, and it will generate a reference or output voltage used through this IO 13 pin on this test port. So ultimately, our aim is to measure this voltage at this pin of this test port, which is connected to the output of bandgap reference inside this IC. So this is our main requirement from this measurement. And obviously, ideally, since our requirement from a bandgap reference is like we want to make it constant or stable around process voltage and temperature. So for temperature, the temperature around this setup needs to be varied, but it's not possible to do it in ambient condition, the kind of environment like room temperature environment or office environment you are setting. For that, a specialized temperature control chambers are used in a professional environment. If you go to some lab or ATMP unit, if they are doing testing and on like temperature control testing, so that kind of setup is required, and then only you can check the performance of bandgap reference circuit with respect to temperature. But in our case, we will just try to see the variation of it with changing that supply voltage, that is DC VDD. So we will see if we give it 5 volt, if we vary it to 4, 4.8, 4.5, 4 volt, whether anything is changing at the output. Ideally, it should not. So these two testing are involved. And by process, I mean, for example, when the fabrication of this die inside this chip is happening. This die is extracted from a particular wafer, and that wafer is part of a particular lot of wafers which get fabricated or processed inside a foundry. So, for example, inside a wafer, there can be 1,000, 2,000 such dies. So, if you want to check the variation of process, you need to do the measurement on all those dies. And similarly, you want to do the measurements on wafers which have been processed at different times inside a foundry containing this design. So that's where you will see if there is any effect happening on your design due to the process, and if the bandgap reference circuit is giving a constant voltage across the process variations in different die samples. So that requires a very sophisticated setup. So for that kind of a testing, extensive testing of ICs or integrated circuit, we have specialized unit. I think I mentioned about in my initial lecture. Those are called ATMP unit. So the main task of these ATMP units is they have a professional setup where like large number of wafer level testing or IC or die level testing or package level testing on huge amount of ICs or dies or wafers can be carried out. So you need that kind of an environment to do extensive testing of this circuit. But today we will just try to vary the voltage of this circuit and see what kind of a performance we derive from it. Okay, so this is the test port, and these are the connections made as per the like the pin connection diagram or the table given here. So these connections are made, and these are the specific connections made, like connecting the VCD pin on this board with the V plus and this down arrow or the ground terminal on the board. So similarly, all other connections are made of the power supply and the output, which has to be measured on this IO13 pin. Next, we will see how to open the waveform software and make the setup there. That is to apply the supply, to apply the DC voltage, that 5 volt supply to this circuit, and then see the waveforms. And the methodology we will be using is to just vary the voltage between 4 volt to 5 volt and see if anything is changing at the output voltage of this bandgap reference, which we expect to be around 1.2 volt. So that is what we want to see. Okay, this is how a waveform software looks like. So I think I will quickly skip this slide because I want to show you a live demo by sharing my screen. I have made a setup at my end. I have connected the board and also the digital device and all the connections. So just these are some of the slides which capture the steps which needs to be followed while making the setup. So since I am sharing these slides on Slack, this will be helpful for you to prepare yourself whenever you want to do the testing on these circuits remotely by booking the slot. So these are for your reference. Just go through this slide whenever you are planning to have a remote testing session with me. And this is how the output voltage will look like. We will just see it in a live demo. And this is an auto set option. I told you, like, if after making all the input and output setups and enabling all the signal, we need to use this auto set option so that it will automatically adjust the settings of oscilloscope and waveform generators, and all the scales will be appropriately adjusted. And this is last slide. I wanted to just give you a feel of this setup, how it actually looks like. So this is the test board. This is the chip on this board. And this is how power supply to this board is given through this USB connection of the laptop, my laptop. So it can be easily powered. You do not need external power supplies, big bulky power supplies to power this board. And then this is the measurement device. And this is also powered through a USB-C type cable. So this is a normal USB port and this is a C-type USB port. So both these can power these two, basically a board and measurement device. And these are the budge connectors which are used to make all the connections from measurement connection from compare 83 measurement device to the test board. And this is how a waveform software looks like on the laptop. So just I want to again emphasize like this kind of it is a very convenient kind of a setup and solution, which I think anybody, if he has access to this equipment, he can do it at own on his own end. But again, I'm again like emphasizing this is good enough for making like a limited kind of measurements when the number of signals involved are less, like one or two analog signals are required, or like power supply is only 5 volts. So those kind of measurements, it is good enough. But if you have a design or a chip or board where you need multiple signals and also the power supplies are involved or more, then I think you need some the proper devices or some other solution for that. Okay, so I think now let me move to the actual window. And so I hope you are able to see my waveforms window. Can you please confirm somebody? Are you able to see it? Can you see the waveforms window? Okay, thank you. Okay, so this is the window, and I have made the setup at my end. So as I showed yesterday, first thing to start is to apply the supply voltage. We need to apply the proper supply voltages to our to the circuit. So I will open the supplies menu, and my circuit is not like bipolar, so I need not use this negative supply. I will just disable it. I just require one positive supply from my circuit, and that to 5 volt. So just select 5 volt. So as you can see, there are no voltages available more than 5 volt here. So my maximum supply which can be provided, or the signal which can be measured, is can only be 5 volt from this measurement device. Just apply the supply voltage. Okay, so we will not enable it before we make all the settings. So once all the settings are done, then only we will enable the power supply. Okay. So once the supply is done, so in this case, we don't need any kind of input signals like any DC or sinusoidal signal. So this wave chain feature is not required. This was used in previous two measurements, that of common source amplifier and an operational amplifier. But in this case, this is not required. I think I clarified that point in my slides. So we will not use it. And just we want to see that is output voltage on, and that for that we will open the scope menu. The scope menu will open up. So I just want to see channel 1 because the output of my design, the IO30 pin on the board is connected to this channel 1 of 83. So I don't need this channel 2. Now I will enable this supply voltage. So my circuit on the chip will get active. Now it is applied. And before making the measurement, I will do run and do that auto set. Okay, so once auto set is done, this will automatically make the measurement and setups. And this is how the waveform looks like. So I think the scale I need to adjust properly, the scale per division. So I will change it to, sorry. Okay. So this is how the output of bandgap reference looks like. I will just stop it to stabilize. And this is you can see on the left hand side it shows 1.20. So this is voltage around 1.20 volt, and there are some ripples on this circuit. So the reason for this circuit could be because okay, I think I will try to explain it. Inside the chip I am using a digital pad to take out this signal. Although this is an analog signal, but I am taking this signal out from the chip through a digital pad, and that digital pad is powered by a clock. So this is, I think, what is happening. The clock is interfering with this digital signal, this DC signal, and it is interfering and like causing these ripples to form on this DC voltage. If I would have taken a analog pad there where there is no digital circuitry involved, so this would have been a constant DC voltage. But now also we can see this ripple is, let me just try to calculate it. So this is around 250 millivolt kind of a ripple. So this is around 100 millivolt, I think. It seems like, yeah. Yeah, this is 100 millivolt delta. So this is like a 100 millivolt peak to peak kind of a ripple on 1.2 volt DC voltage of a Bandgap. So this is most probably due to the pads, because this chip includes a lot of digital circuit on it, and there are a lot of clocks involved, and this pad is also digital, through which a clock signal is getting basically ramped up on this DC voltage of a Bandgap reference circuit. So that's why this is coming. Otherwise, it would have been a constant straight line DC voltage. Okay, so but our main uh, thing to look out is like whether this voltage, DC voltage, remain constant if I change the supply voltage of my circuit or Bandgap reference circuit. So this is 5 volt. I will just change it to maybe, let us gradually do it, 4.8 volt, and then see what happens here. Okay, so this remains pretty much constant, doesn't change. Now let me again change it to 4.5. So here I think it remains around 1.2 volt, but I think it has reduced a little bit, but still it doesn't make much difference. I think it is around 1.2 volt only. Even though I have changed the power supply to this circuit by 500 millivolt, like 10% I have varied from 5 to 4.5, 500 millivolt I have decreased, but still the DC voltage of this circuit remains constant. Now let me make it 4.3 volt. And now it has further decreased from like its central line to 1.19 or something. And now let me make it 4 volt. Let us see what happens to, although it is too much for, I don't expect the circuit to work at this voltage. But still, it remains around 1.2 volt. So this is pretty good. Like I think from 5 volt to 4 volt, the power supply of this circuit has changed, Bandgap reference circuit, but it is still giving a voltage around 1.2 volt. So if this kind of a voltage is going to some operational amplifier or some LDO circuit, so even if the supply voltage is varying from 5 volt to 4 volt, the performance of that circuit or specs of that circuit won't deviate much from the expected value. So this is a requirement what a Bandgap reference circuit needs to fulfill for the biasing on that analog circuit. Okay, so let us just try to reduce this further. So at some voltage, it will stop giving this voltage. Let us see where that happens. 3.8. It is still pretty good. Okay, so now here it is. Okay, so now it is getting low and low. I need to change the scale. Okay, so now it has reduced a lot. It has come around 0.2 to 1.2, around 0.8 or something. So here it is starting to deviate from the required. So now it is further reduced. So as you can see, we started with 5 volt, and this DC voltage of this waveform was around 1.2. But as I kept on decreasing it to 4 volts, so it pretty much remained constant. But beyond that, it is now getting decreased further and further. So basic thing to know is like even after, so generally whenever we design any circuit, integrated circuit, we take, like there can be a deviation of plus minus 10% in the voltage, and within that range the performance of that circuit should not deviate. And so from bandgap reference also, we generally expect, like if 5 volt is my ideal, like a VDD voltage to be given to that circuit. So plus minus 5 or plus minus 10% means 4.5 to 5 volt. Within 5.5 volt, this circuit should remain constant, like the output voltage should not vary. So this is what I think this circuit is performing. So basically this is what I wanted to show you, like how a bandgap reference circuit is like working, and how what is needs to be checked here. So this kind of measurement which we did is just with varying the power supply. So there are two other factors that is in PVT. As I showed, this process, voltage, and temperature. So we did the measurement using voltage variation, but the process and temperature require some other factors. But for process, it means you need lot of samples of this kind of a chip, maybe 1,000 2,000 chips, which have been fabricated on different wafers and in different lots, and then try to do the measurement on those and see if they, from lot to lot or from die to die or chip to chip, is there any variation happening in the performance of bandgap reference circuit. And for temperature, obviously we need to put this setup in a temperature controlled chamber where the temperature of that chamber can be varied, and then we can do this kind of measurement. So those things are not possible in current environment and setup, but that is how complete extensive testing of this circuit, or for that matter any analog circuit or any IC, is done. So I think that's what I wanted to share with you today, and it's all for bandgap reference. Any queries are there, we can discuss it. Any questions from your side? Any questions, you can please put it in the chat box or Q&A menu. If you want to ask anything. And I think most of you have joined the Slack through the link which I shared. So for benefit of anybody new here, I am again sharing the link of the form to get the invitation of Slack channel. And also I am sharing the link of where you can book the slots for testing. So this link also I have enabled today. So if anybody, I think all the slots are available on this link. You can please go to this link and book your slots, and also select the circuit which you want to test. So that also I have shared in the chat box. Okay, I think we can conclude for today. If no queries, you can, if anybody has any query, you can please put it on Slack. Now the slots are also open, so you can book your slots, and we can, if you have any queries, we can discuss it on that day whenever your slots are available. Okay, thank you very much, and have a nice day. We'll meet tomorrow for our last lecture. Bye.